morning, everybody, with the usual caveats about location.
We had a fun session this morning with 2 or 3 people joining the office hours, just going over what how you look at interferograms, and how to distinguish noise from signal, and kind of focused on phase unwrapping type issues and things like that. So that was, I think, instructive.
Excellent.
Actually had more students than instructors.
That's cool. Their last chance. Although I guess if people still have problems and they're going to the InSAR meeting next week, then possibly we can help them.
That's true.
I showed a little bit of how to use the MDX program that is excellent, but doesn't run under the notebooks, so we can't put it into the notebooks.
Big fan of MDX. It's been my constant companion since graduate school, all the way to now.
Well, before that there was DGX. You probably used DGX when you started.
We had some kind of weird NV code actually that Tim Wright used that came from I don't know where. It was written in French though, so.
Yeah. Well, we actually do have an MDX replacement that works on cloud instances. It uses more modern HTML5 protocols, but it's not quite ready for prime time. It's almost there, but it has a lot of the same functionality. I think it's missing. Yeah, it's really quite nice. It's faster than MDX in many cases.
It does all sort of the clicky things like click and get the values and all that sort of stuff.
Yeah, it has some of those features in there. It doesn't quite have all of them, and but it has other features that are nicer. It has a little zoom window so that when you click in a spot, it zooms right around that point, and you can sort of do a vernier correction motion so that it will get on exactly the right point you want, and then you can click on it. You can draw profiles in a much more systematic fashion, I would say. And,
could you define polygons?
It doesn't quite close the polygon yet, but that is on the to-do list. It's on GitHub, actually. You can, on the public GitHub, and you can get it yourself if you want. So it's kind of a bear to install, so I wouldn't recommend it, but you can at least see what the issues are. The issues are the features that are not there yet. And I think you'll find a lot of the things that you are requesting now that are not in there are already on the issue list because I put them there. They are things to be done in the coming months by the developer, who's a kind of a brilliant coder, who's a contractor, not a JPLer.
Cool. What's it called?
It's called QED.
I will look for it.
I think you showed that to me before, QED, or somebody did.
It was part of the last InSAR science team meeting demonstrations. And it does work on the cloud instances that we've defined for the JPL science or the NASA science team to use. But and you guys could install it on OSL if you wanted to try. It's not trivial.
Yep.
But that would be a good thing, good exercise, because then for this class or other similar classes, you have an MDX-like capability for.
And that's is that open source? Yes, I'm assuming.
Open source, yeah.
Yeah.
Get it right now. The thing is, you need to install 2 other packages, a build system called MM and a framework called Pyre. both of which are part of ICE 3 already. So I mean, you kind of, it's something that one needs to do, but that takes a little bit of care and probably not for the faint of heart, which you guys aren't. So you can do it. I'm sure you are able to do it.
Not on Condaforge is what you're saying.
It's not on Conda, although that's another thing on the issue list for Empire. They need to be Conda installable. I'm told that they are close to being Conda installable, but once they're Conda installable, then the installation of QED then becomes trivial. So that's the process. We're getting there. The contractor, unfortunately, is the kind of guy who gets you like to the 95% level and then just gets distracted by other things for whatever reason. I think it's a strategy for making sure contracts keep coming somehow. So he's now working on another task that he has prioritized for the next couple of months, and hopefully we'll get back to my priorities in the fall.
Nice. Okay, we got about 40 people on now. Does anyone have any things they would like to ask? Any questions? Any issues with homeworks? Anything they'd like to show us? Please either unmute yourself or put it in the chat and we'll get to you. So here's a question. What is the deadline to submit all required assignments today or tomorrow? I mean, realistically, all of the instructors are going to be at the InSAR Science meeting next week, and very unlikely to be looking at everything in much detail until that is over. So until the end of next week, I would say.
You're giving them a lot of outs. Yeah, so the end of next week, we'll have the environment run for at least another week. So you can use that time to finish all your work. Also make sure that you've downloaded all the stuff that you want to keep. But yeah, so you don't have to have all your required assignments done today. Note also that if you are interested in the certificate, we are requesting that you submit 6 of the 10 at the very least. So please keep that in mind. And if you are one of the people that signed up for credit, you have to submit all 10 of the assignments, and we'll actually look at them and make sure that you did the work correctly.
And we'll have a post-course survey prepared by the end of today that you would also be required to take. Okay, there was a question. When computing the displacement from an interferogram, is that normal to count all the phase change factors, or can we do some simple judgment based on the interferogram that some of the phase change, such as the atmosphere, are trivial, so that you don't have to take those into account? In my opinion, you don't necessarily know a priori what all of the phase change is due to, even though it may look like atmosphere. Typically what we would do if we were modeling would be to unwrap the whole thing, including the noise, and then try and fit the model and look to see if the residual fit to so what you get when you take your model away from the interferogram looks like noise. I think it's quite, unless you have a very, very low level of signal in your interferogram, it's very hard to tell what might be the signal in that.
It's also going to depend a bit on what science question you're trying to answer. For instance, if you are, so Eric Fielding is in the room, he's done a lot of work on landslides. And if you work on landslides, you know that the signals you are interested in are fairly localized. And it may allow you to use certain spatial filters to remove long wavelength signals, for instance, from the data set that you are most likely not interested in. So depending on what your science question is, you might be okay with applying certain high pass filters, for instance, to simplify the phase signal without actually distorting your signal of interest. But it's very specific to the kinds of applications that you're working on, and you have to be careful with any of these filters when you apply them. Another thing that's happening is in the community is that various groups have been starting to think about using deep learning methods to try to denoise certain data sets, either extract signals of interest or remove certain nuisance signals to various levels of success. But that's certainly still a research topic.
It's a cool one, especially, yeah, in machine learning, what noise looks like. That's definitely a hot.
Yeah, we have a project on that that I'm involved in.
I have one through SCEC that hopefully.
And if any of you has ever looked at some of these large-scale deformation maps that have been published in recent years, like Norway has a large-scale deformation map that they published that covers the entire country. They are typically in some form filtered. I think for the Norway map, because they're very interested in slope motion, they've applied some sort of a low-pass filter effect to remove long wavelength signals. So yes, there are certain things that can be done if you are very clear with what you're looking for.
And then there's the European ground motion monitoring service. That's the whole of Europe, where they used GPS or GNSS data to control those long wavelengths where InSAR is more noisy. And they may have actually processed the local area, removing the long wavelength atmospheric noise, and then added it back in the GNSS based long wavelength deformation. So those products are really impressive because they've done this integration of the GNSS measurements with the InSAR data.
Okay, so there's a question here about AutoRift. I don't know if you can see it, France. That's probably for you. If I don't take TIFF files from ASF and I need to process my own Sentinel-1 images, how do I do that using ICE?
So in the end, I can't actually remember if they are. Did he explain the workflow and say if the AutoRift is done on the SLCs or in ground range? Did he say that?
He showed the automated system on ASF. On
right. Yes. Yeah. So there. So we did start by processing Sentinel-2 data. So I think it's done in ground range. So the way you could do it is you could just use ICE to geocode an image or a pair of images, ideally from the same track and frame, and then export those as TIFFs, if, for instance, or change the code that reads in the data. So right now the code is assuming that the data are in GeoTIFF, but that's not a necessary step. If you have an HDF5 or a NetCDF file, you just have to change the way the file is being read. And this is all based on amplitude images, so there's no InSAR involved in this case. You would geocode a pair of images and then run it through AutoRift to identify features and track them.
Any reason for using the near-infrared band to generate ice velocity in AutoRift? I guess that's again speaking to yesterday's exercise.
Right, and I'm assuming that they found this to be more useful band in terms of saturation and amount of detail that it preserves over very bright surfaces such as glaciers. I am not entirely sure why that was picked, but I could follow up with Alex Gardner, who's developed the AutoRift processor, why he used certain bands for certain sensors.
Because I would have thought the panchromatic band would be a good choice.
Yeah.
Given it's
I do not know. I have to. I can't follow up.
Higher resolution.
I did share. There was a question about the Norway map. I did share that on.
Yep.
think there's some issue with the map right now. No, did they expand it to Sweden? Looks like it.
What's the
Yes, I
minimum
think
number?
it now includes actually Norway and Sweden. And I'm also going to quickly share the European Ground Motion Service map if you haven't seen that yet.
So you don't need to run the processing all the way to the interferogram to have a successful or to use AutoRift, right? You can actually specify in the XML file for TopSap that you just want to produce the SLC and geocode it, right?
Yes.
There's a produce interferogram. I can't remember what the actual option is called, but you can say false and it won't make the interferogram.
And Paul and Eric are probably more competent speaking about how to get to a geocoded SAR image using ICE.
There's an RTC app, but I'm not sure if the RTC processing would remove information that you'd want to keep it for AutoRift. The RTC is radiometric terrain correction, as Franz is an expert on.
Yeah, so if you have AutoRift questions like this, please, if you haven't done so yet, post them in Slack, and I'm going to make sure that Forrest sees them. Forrest works on AutoRift, and he is in a better position to answer those.
Can we require pixel-wise incidence and heading angles for the decomposition of line of sight deformation? It really depends on sort of the scale of the thing you're looking at, and also how precise you want to be. I showed an example for the landslides in Berkeley where I just assumed that the line of sight was fixed, and that's okay because really we're only looking at an area a few kilometers across. If you're getting to larger areas, like tens of kilometers, then there will be an appreciable change in the line of sight vector across those sizes of area. And so you might want to actually use full resolution pixel information for line of sight. And that is provided as this LOS RDR file in ICE, and there are similar things that are provided in the geometry file for MintPy that we'll meet today. So you can do it. And if you just used a fixed line of sight and you looked at a sufficiently large area, you'll actually get a ramp across your image sometimes because you're not accounting for it. That change. I see more AutoRift questions. How to translate a VRT format file to a TIFF format file using GDAL translate. Kindly put the command here. Well, the command is in the GDAL notebook, 0.4, I think it is. That whole exercise. It's a very short command. I think you just have to specify what output format you want, and it will do most of it for you. You can also look at the GDAL help pages. There are extensive online examples on their own website of what the syntax is.
On the AutoRift accuracy of the co-registration, you can actually calculate the accuracy of co-registration if you have a point target, if you sort of think of a big rock on the glacier that you're tracking. So there's some bounds you can create in terms of the accuracy of the product you create. For most targets, which are not point targets, it's a little bit hard to say. One thing you could do is when you look at the co-registration or the cross-correlation peak that you're creating, you can measure the width of that peak to get an idea of what the accuracy of the product is. I think AutoRift does deliver the formal product and accuracy layer, as far as I remember. But it's usually not as high in terms of the offset accuracy as, for instance, TOPS processing, phase-based co-registration that's done for some of the InSAR processing routines. So I would venture that it's a fraction of a pixel, somewhere between a pixel and maybe a tenth of a pixel in accuracy, depending on the specific target.
Yeah, and I would like to add on that. from the paper from DR, they actually wrote an analytical equation. So the accuracy, you can calculate that based on the coherence of your SSE pairs in terms of SAR, and then and also based on the estimation window size you used to do the cross correlation. And in practice, remember we have a parameter called oversampling. That oversampling determines how precise you can measure in terms of the output. So you will want to make sure that your oversampling factor is at least slightly higher than the precision that you want to measure also.
See, I think I had a slide somewhere on the accuracy, but I see if I can find it. So I have a slide. So you can for sort of feature tracking algorithms, if you do them on SAR data. One big advantage of using SAR over optical data for these approaches is you can track speckle. So if you have data sets that are coherent, it means that the speckle pattern, which is a very noisy spatial data pattern, is staying coherent. And the same, and you can track the speckle pattern even over features on the glacier that are actually not having features themselves. And for speckle, if you have if you're tracking speckle pattern, you can calculate the accuracy that you can achieve in numbers of resolution elements. And so that's probably the equation that Yunjun referred to. And so it's shown here. And then it depends on whether you do the correlation only on amplitude, which is what actually AutoRift is doing, or if you use the complex information, so the amplitude and phase for tracking. And so amplitude only cross correlation provides a little bit lower accuracy, but more points. And complex cross correlation provides a bit higher accuracy, but usually less number of points. So AutoRift is choosing amplitude, it's faster and gives you better spatial coverage, but you surrender about square root of 2 in accuracy. But you can see here you are, depending on how coherent the speckle pattern is, at about 0.2 or a tenth of the resolution cell. If the speckle is coherent and you can track it. So for that, you can actually calculate the accuracy using these equations. And you see that here on the plotted as a function of coherence.
More questions? We have a few more minutes before we unleash Paul on you with details of NISAR.
Well phrased.
Did anybody do the ionosphere correction processing? Yeah, nobody has any questions about that apparently.
So clearly explained.
You explained it well.
Well, Paul will be talking about ionosphere corrections with NISAR in the next, to some extent.
Oh, there's a question.
Not a lot. It's only 20-minute talk. So
What software can we use to do complex cross correlation? I'm assuming that ICE has a module for complex cross correlation. It has AmCore, which is amplitude cross correlation.
Oh.
I don't know if there's one included. Some software packages is like, if you have the money, Gamma Remote Sensing has a complex cross correlation module. You could also program it yourself if you wanted to, using the complex data. In most cases, you're fine with amplitude cross correlation.
Yeah, so the AmpCore program, I think does only amplitude, even though at one time it did both. We found that oversampling the complex images by a factor of 2 and then detecting them as amplitude images, and then doing the AmpCore amplitude correlation got you, if not the identical results to complex correlation, you get very close. So we just sort of focused on that for whatever reason. I think the GPU version of code in ICE2 for AmpCore does do both, if I'm not mistaken. Maybe you know better than Yunjun.
Yeah, the current version on the public does not have it. Li Jun actually has implemented a coherent one that we are actually currently testing.
I see. But you know, from a practical point of view, I don't think you need to worry about it very much. Amplitude cross correlation of oversampled images is pretty good. About as good as you can get.
The question, why does ASF's on-demand products use gamma instead of ICE?
Yeah,
It's a good
France,
question.
why is that?
Huh?
You're not a team player?
I'm not a team player, that's right. No, so ASF has used gamma for a very long time, so we had a more track record and heritage information on gamma. We are actually working with JPL and a couple of access projects to on-ramp ICE-based products. We have already integrated the ICE ConW, the geocoded unwrapped processor into the platform, and we are transitioning slowly over to ideally ICE3. So in the near future, when all of the functionality for ICE3 is available and tested, we will switch over to ICE to remove dependency on licensed software packages. So for now, it's mostly because we just had all the tools in place and we could do that faster. But we are intending to move over to ICE3 in the next year or so.
I think Franz, you're being generous. Gamma is a commercial package with people behind it who will pick up the phone on their end when you call them with a question, and has documentation and customer service that is appropriate for a commercial package. A lot of the developer, at least the prime developer, actually used to work at JPL in the early days, and a lot of the same methodologies were employed in Gamma. So it was, I think, from ASF's perspective, a high quality and reliable package that they could use as a DAC to provide services to customers. I think that's a little different from a community sourced package like ICE2, which was never intended to be a commercial package. I think it was the right decision. Now with the InSAR mission, I think we have a chance, and the maturity of ICE2 and coming ICE3, I think there's a chance to go with this other methodology without necessarily using Gamma. But it's, if you can afford it and you need reliability like that, it's a great package.
And it's also, the community has done cross comparisons of some of these packages that are out there now. So ICE and GMT-SAR, which is another free, very capable InSAR processing package, and Gamma, and all of those have been cross compared to each other. And I think the conclusion is that from an end user perspective, if you are harvesting interferogram products, you shouldn't have to worry too much about what software package was used. They all are high quality these days, and they all provide you with a scientifically valid InSAR product.
Okay, we've made it to 10:30.
Shall I start then?
Yes, please do, and we can carry on answering questions in chat.
Alrighty.
They come in.
All right. So my job this morning for 20 minutes or so is to give you a quick overview of an ISAR mission. It's still coming up on my screen. Hopefully we can see it now. So ISAR is an enormous team effort. It's a partnership between NASA and the Indian Space Research Organization, ISRO. That's why the name evolved to NISAR, the NASA ISRO-SAR mission. And on both sides of the Pacific, in NASA and the extended community of contractors and our science teams, it's thousands of people at some level putting together a very large system. So I'm talking, but this represents the work of many, many people. So this grew out of a community request to NASA through the decadal survey process for a mission. This was back in 2007, actually. It's taken this long for NASA to
Did I lose you guys?
I don't hear anything.
Okay, so it's Paul that we lost, I think.
Yeah, I think we did.
This is what you get when you live in a state that has so terrible internet connection like California. So short break. While we've lost Paul, there was a question about should one learn all the software packages that are out there or focus on one and master it. I would personally focus on one and master it. The open source tools that are out there, they're all very, very capable and have but if you wanted to use them to their fullest capability, it will take a little bit of time to learn all the details. So I would rather focus on one and get really proficient on one. I personally think ICE is a good choice for that because there is a commitment through NISAR and through the DAX to make sure that this software package gets further developed and is maintained. If you dive deep into ICE, I think there's some likelihood that you will be able to use ICE for a long period of time into the future because of these commitments.
It looks like we lost Paul completely, so I'll keep an eye open to let him back in, but do we want to move on to something else maybe?
Should we, is the slides on GitHub? I mean, I could jump in until he comes back. Let me pull them up real quick.
Go for it.
I'm assuming that he's only going to be out for a very brief period. So let me pull up the slide deck. Or, Eric is on the team at JPL. You can also take over, Eric, if you want to. Oh, the slides are not on. Are they on GitHub? Maybe you have to restart.
Yeah, I thought there was a
Yes, they are on
a
GitHub.
pull request from
Yeah.
a couple of days ago.
I have to restart my server. Hang on. Starting. See who wins, Paul Rosen or my OpenSAR Lab instance.
There's a question about ICE licensing.
Yes.
As far as I'm aware, ICE is open source, so there is no.
Yes, so the ICE used to require a license until maybe 2 years ago. Is that about right? But 2 years ago, we were able to make sure that ICE is fully open source. So you don't require a license for ICE anymore.
I guess the question is it possible to use it for commercial use?
And I think the answer to that is yes.
Yeah.
It has the Apache license, so it does allow commercial use.
Okay.
It's not a, like the GNU public license.
Okay, so I think I have the slide deck. Do you want me, should we wait a few more minutes for Paul, or should I just?
Start, and then we can tell him where we got to.
Yeah.
One of the major developers of ICE now works for a private company, so I'm not sure what they use, but they may use some parts of ICE.
Okay. So sorry about the delay, and I'm gonna do a very poor stand-in for Paul, but maybe with Eric's help, we can pull this off while we are waiting for Paul to come back.
Paul might have lost power at his house or something. We're on regular day off today at JPL, so he was calling in from home.
Yeah. Anyway.
Oh, so yeah, he said he lost connection. He's trying to get him from the phone, but in the meantime, he can get started. So Paul Rosen, who was on the call until recently, he is the project scientist of the NASA ISRO or NISAR mission, which is a mission that is being built and launched by JPL together with the Indian Space Research Organization ISRO. The launch date is currently January of 2024, and hopefully will stay at January 2024. Oh, Paul Rosen is coming back in. Paul. Did somebody let him in?
Can you hear me?
Yep.
Yes.
Yes.
Do you want, I have the slides up. Do you want me to just show the slides while you talk?
Yeah, that's fine. I'm now on my MiFi because somehow my Wi-Fi went out. So I'm sorry about that. It's Murphy's Law. Whenever I'm at home and I need to do something, somehow the Wi-Fi decides it's time to cut out. Okay, so go on to the next slide. I don't know. Did you hear anything?
Just the first few words, I think.
Just that there was a lot of people involved.
Okay, very good. So second slide is about the science requirements for NISAR. So as I was saying, we started with the science community recommendation back in 2007. The decadal survey of 2007 recommended a SAR mission that had capabilities to address questions that you see on the screen here in three principal science discipline areas. That is, in the cryosphere, understanding the dynamics of ice sheets, mountain glaciers, and sea ice, trying to understand the relationship between ice motion, ice variability of motion, and climate forcing and interactions. Another discipline was ecosystems and biomass change, in particular, again, focusing on climate-related issues, how the changes in above ground biomass and wetlands affect the carbon cycle and what that means for climate. And then in the third discipline area that was focused on in the decadal survey, solid earth deformation and hazards. Can we understand better through geodetic imaging measurements from a SAR, the nature of fault systems, how they interact, how stress is transferred from one part of the system to the other during earthquakes and in between earthquakes and that kind of thing, as well as for volcanic systems and other natural disasters. There's also a component of urgent response associated with this recommendation, trying to use these measurements to help mitigate disasters as well as monitor them as they evolve. As you know from this course, there's lots of ancillary measurements that can be made beyond this that are useful scientifically and for applications. Hydrocarbons and water withdrawal from subsurface is an active area of usage of SAR data. And I think you've seen some examples of that in this class. Since we're partnered with India, they also had a number of other objectives associated with processes in and around India. And India tends to focus on more operational applications anyway in most of their space missions. So they're very interested in coastal processes, both on the shore and offshore, shallow bathymetry, coastline evolution, as well as ocean winds that are indicative of you know, sort of the hurricanes and typhoons that come onshore, where they're going to go, and for prediction of flooding and that kind of thing. You can see some examples of the kinds of temporal variability that we're trying to capture with a mission like InSAR, where top left is an earthquake, coseismic signal. The middle left is a temporal change in water inundation in a particular area in India where color represents date. So you can see how dynamic the shoreline is in this inland area. Then the bottom is a wildfire evolution through monitoring the change in the backscatter over time and the coherence. So these are the kinds of things that we are hoping to do with InSAR. Go on to the next slide.
You
Next
should
slide.
see the next slide.
I don't see it yet. There it is. All right, so this is a major partnership. Without India, we couldn't have done this mission, and without us, I think India would have a hard time as well. You can see how the mission is divided up in terms of responsibilities on the hardware. The US is providing everything that's sort of labeled in green, including the mechanical octagonal cylindrical structure you see labeled radar instrument structure. All the L-band electronics, that's 24 centimeter wavelength electronics associated with the L-band radar, the boom and the reflector, and the GPS, that's all contributed by NASA. The bus itself that powers the whole system and navigates in orbit, as well as the launch vehicle and the S-band radar electronics is all provided by India. So it's an enormous contribution. The L-band part of it is larger physically than the rest of it, but it's very highly balanced. You can see the mass is quite high, it's 2,700 kilograms, and the power is also a pretty high power system. So it's a very big system. Next slide shows what we're doing for mission operations. I think you skipped one. Yeah,
Sorry,
maybe I should try sharing my slides again.
Yeah, let's see if that works. Yep.
Yeah. Now that I have the Wi-Fi, it seems to be working. It's this one. So, yeah, I think you skipped one slide here. Okay, so going back a couple of slides, this just gives you an overview of the attributes of the system. So it's an L-band and an S-band system. I already talked about that. The L-band is for good correlation, as we've talked about in this class, and foliage penetration so that we can measure the woody biomass for the ecosystem's objectives. S-band is sensitive to lighter vegetation, but also has good coherence, almost not quite as good as L-band, but pretty good coherence for interferometry. We use a technique called SweepSAR to get a very wide swath with fine resolution. I'll say more about that later. It's polarimetric, and we'll talk about the polarimetric modes later as well. Exact 12-day repeat, similar to Sentinel-1, with a variety of resolutions available to it. Does somebody have a question?
There are some questions that are being addressed, but maybe we are not seeing it in presentation mode. If you, that may be intentional, but if you want to go to presentation mode, we see it bigger.
I don't know how you're seeing it.
We see basically your PowerPoint screen.
Let me just share my screen.
Now we see a
Sure.
presentation mode, I think.
I'm going to share my desktop. Hopefully that, oops, don't click the leave button, leave meeting button. There. So now if I go like this, how does that look?
Okay, we are waiting, I think. Yes, now we see it full screen. Great.
All right, sorry about that. This is not my big tool of choice. Anyway, we operate for 3 years according to NASA's planning cycle, but ISRO has a plan for at least 5 years, which means that we will be going 5 years, and it may go even longer if the resources are available for controlling the spacecraft, hydrogen on board, as well as the health of the instrument. We have great pointing and orbit control so that we can do short baseline interferometry for deformation. And one of the nice features is the L-band has at least a 50% duty cycle, meaning we can completely cover all land and ice all the time that's visible. So we get global observations, and at S-band we can cover all of India and the surrounding areas and much of Antarctica. One unique feature of this mission is that we look to the left instead of to the right. So we're looking more towards the South Pole than we are towards the North Pole. For those interested in the Arctic, of course, that's not so great, but there is Sentinel-1 providing very reliable Arctic coverage. So this gives uninterrupted time series for scientists interested in time series for interferometry, and it gives sort of unique comprehensive coverage of Antarctica. So I already went over the slide here, so I'll skip that one. And I was getting ready to talk about the operations overview. This is a complicated slide. Hopefully it showed up for you already. So I won't say too much about it, other than the fact that we have both the L-band data and the S-band data. They come down through to 2 different sets of receiving stations. The L-band data goes to NASA stations, which are at Alaska Satellite Facility, as well as in Svalbard and other places. And the S-band data goes down to ISRO stations in both India, Srinagar, and in Antarctica, where they have stations. You can see the volumes of data here, 35 terabits per day for L-band data, 8 terabits per day for the S-band data. So huge quantities of data. With separated pipelines and separated processing chains. Just to give you a sense for where we are in the development, we are now at this point, we are in the final stages of integration of the payload, and we are now in the thermal vac chamber doing the final testing of the integrated payload before we ship it to India. It will be shipped at the end of this year, beginning of next year, to India and go through integration with the spacecraft, and then we'll launch in early 2024, planned January, late January 2024. And this just shows you what the hardware looks like. On the left is the test of the mechanical boom and reflector subsystem on a facsimile of the actual flight electronics. It's just a mass mock-up on the left. And so it went through thermal vacuum testing earlier for risk mitigation. On the right, you see the actual flight system fully integrated with the electronics, the engineering payload, which is controlling the electronics, as well as the boom and reflector. And this is what's now in the thermal chamber. So a very exciting stage of development now, and everything's finally going better now that the pandemic is over and some technical issues were resolved. So as you know, SAR is quite versatile. We've talked a lot about interferometry in this class, which is what we have at the bottom. And we talked about the applications, geophysical modeling, subsidence, inundation. People are using it for a whole variety of applications wherein you can use the phase change to measure surface displacement. In the polarimetric area, which we haven't focused on much in this class, you can use the different polarization states to say something about the nature of the scattering from the surface, which then tells you something about not just the surface, but how it might be evolving in time. So different signatures of polarization indicate different surface types. You can see that when you have HH and VV sort of equally weighted, you get sort of a soil-like signature. If it's VV only, it tends to be water dominant. When it's vegetation, the cross-pole term transmitting H and receiving V is dominant, and so forth. So you can use this for a whole variety of land cover type and land cover change type applications. So the measurements we make are repeat pass interferometry and polarimetric diversity. And that's kind of what I just said on the previous page. These are the measurement types that we have. And I think I don't need to spend too much time on what the capabilities of using these for geodetic imaging is. Here's just an example of a time series. You'll see lots of time series later today. Of the Los Angeles area where water is being withdrawn from the surface in the summertime for use in irrigation and other purposes. In the wintertime, re-injected. So you can see this seasonal motion of the surface as water is extracted and then recharged. In addition, there is a long-term secular deflation of the surface due to the fact that the recharge is not complete. So you can see these very subtle, these are inch or centimeter scale deformations over a long period of time using time series analysis. Tells you something about the physics of the subsurface. It also tells you about infrastructure. When you see streets buckling and pipes breaking, you can relate that to this kind of deformation in an urban environment. As you know from past missions, we can make velocity maps. AutoRift is what you were using to make these kinds of velocity maps. These kinds of things now with Sentinel are much more doable. But before Sentinel, these kinds of maps took years and years to produce. With InSAR, you'll be able to produce such a map in Antarctica and most of Greenland in about 3 months. You'll be able to make several maps of this nature and average them together to beat the noise down. So it's really going to not just give you a snapshot of the ice velocity, but also the dynamics of the ice over the seasons and over the years, which will help drive climate models of ice dynamics, which will help drive climate models. And in the ecosystems area, a map like this that you see from ALOS 1 took many cycles to produce. It's still complete. It doesn't really show you so much the dynamics. This is backscatter from the ALOS image, which indicates what the surface type is. The yellowish color is forest, obviously, and this orangey color is inundated areas around the Amazon. The blue is the Amazon itself. This again is a very laborious effort to put all this together. With InSAR, we expect to be able to make a map like this every 12 days from ascending and descending, and then look at the temporal variability of that over the seasons and over the years. There's a whole host of applications, as I indicated earlier. Forestry, as well as biomass estimation. Forestry is something that is very important. Soil moisture is a product we can make from the polarimetric data. Mapping flooding and all kinds of other disasters is something that people are using SAR for, and is great because it's reliable, all weather, day, night kinds of observations. So you don't have to worry about clouds. You can always make some sort of reliable measurement. And as I mentioned, India is looking at the coastal regions regularly for tracking hurricanes or typhoons as they enter waters around India. So we have L and S band. Many people say, well, L and S band, they're very similar in terms of their wavelength. Why do we need these two radars? Well, there's both political reasons or programmatic reasons to have two different radars. There's technical reasons for having the wavelengths not too dissimilar on a single platform. And there are phenomenological reasons for doing it at these two frequencies and having them not too far separated. The examples you see on this page are from the ISCE mission from back in the 1990s. And that was L band and C band. But since the C band is 6 centimeter wavelength and S band is 9 centimeter wavelength, they're actually not that dissimilar, but dissimilar enough that you get some great information out of the S band. But the point here is that you can you get very different signatures in multi-polarization, multi-frequency data than you get with just a single observation. And you can see on the left are wheat fields with this sort of purpley hue to it, and on the right you have rubber trees and other plantation type vegetation, which has a very different signature. So we expect to be able to do this kind of improved land classification using this multi-frequency, multi-polarization data where we're taking it. And also because S-band is a longer wavelength than C-band, we expect its coherence properties to be better. So we can use it for example, exquisite ionospheric correction as well as other interferometric applications. So I'm not going to say too much about this. This is just to say that we have a technique which is first of a kind using digital beamforming and this special phased array reflector configuration where we transmit on the full array, it illuminates the full swath. And then as the echo comes back, we actually track it digitally with this set of receivers. There's actually something like 24 L-band radars, mini radars, and 40 mini S-band radars here, tracking it, digitizing it, and beamforming it to give you the full swath with a very wide swath and fine resolution. There are gaps in the swath that this technique introduced because you can't transmit while you're receiving, but we have a technique that will fill in those gaps, as I explained earlier in the class. And from a user perspective, you shouldn't have to worry about that. So by virtue of having this wide swath and a very fine, large duty cycle, we have an observation plan that the science team has come up with, which is quite systematic. And it should give you both ascending and descending coverage over all these areas that you see at L-band consistently every 12 days for the life of the mission. India and the areas around India will be dual band, L and S band, as well as a number of other places like Indonesia and a good fraction of Antarctica and CalVal sites. There's a possibility to add more S-band data, possibly, but at the moment, those are the areas that we've scoped. So it's a very comprehensive plan. We're expecting to be reliable data everywhere and mostly the same mode of operation over any given geographic area. So you can count on it being there in a fashion that you know. This radar has thousands of possible modes, but we focused on sort of a limited set of observation targets to minimize the confusion for the users and to optimize the time series analysis for scientists. So you can see these are sort of the fundamental modes at L-band. Dual pole, DP means dual pole, SP single pole, and we do have some quad pole modes here as well. QP, should say QP there, but I don't know what happened there. Oh, QP is down here. Somehow some of the text got deleted here. You can see that we have different resolutions for the different targets. And for the S-band nodes, we have a combination of dual pole and circular pole nodes at a variety of resolutions. The sampling strategy is basically to take data all the time. S equals 1p means that we sample every pass. At the higher latitudes, we reduce the sampling because there's a lot of overlap, so we try to save data volume. And you can see most places we observe ascending and descending at the same in the same cycle. So it's a limited set of modes and should be easy to interpret, we hope. This gives a little more detail on the modes that we are planning. You can see there's some quad pole observations over agricultural areas here and up in Alaska. This is probably forests up in Alaska. But we change the mode depending on the science target, and I'll let you study that at a later time. In terms of products, ISAR is also a little bit unique compared to most missions. Sentinel-1 primarily is delivering level 0 and level 1 products. ALOS-1 also level 0 and level 1. For NISAR, we're producing level 1 interferograms and polarimetric covariance products in addition to the SLC data. And that's pretty unusual. Not all possible interferograms, they're mostly nearest neighbor interferograms, but from that you can do quite a bit of science, and we can potentially produce a few more. And level 2, these are all geocoded products, versions of these level 1 products, which is also quite unique. And we will have geocoded SLCs so that you can save the effort of doing the geocoding yourself. This is what's being delivered operationally for all of that data, all of the areas you saw on the previous page. This will be delivered to the Alaska Satellite Facility and distributed through their DAC. In addition, the science team is developing algorithms to validate our science requirements. We have very specific requirements that I didn't go over, but they're measurement requirements, accuracy, certain resolution, at a certain scale, size, and such. These will not be produced globally for cost reasons, basically, but they will be, the tools will be available to the community to use and modify as they see fit. And so we will produce validation products in certain areas around the world where we have ground truth. And those products, as well as the software to produce them, will be made available to everybody. And you can then, kind of like in this class, you can run the test case that we produce, and then you can apply it elsewhere. And that's all being done through Jupyter Notebooks as well. It's one reason why we do this class, is to get the community accustomed to this methodology of accessing and processing data. So as I said, it's 35 terabits of data, raw data, that balloons to something like 60 terabytes per day of science products. So it's an enormous volume of data, something you don't want to be downlinking or downloading from the DAC to your personal computer. That's why this cloud processing methodology is so important. The ICE3 software that this mission will be using is only available on GitHub. As stated earlier, it doesn't have the full suite of capability that ICE2 has. That's why we still use ICE2 in this class. But it's getting close, and soon we can probably transition to an ICE3 based class. And all the concepts, of course, are the same. The level 0 products are raw data. The level 1 products are all of the SLC, interferogram, and covariance products in range Doppler coordinates. The level 2 products are geocoded versions of those. We do have sample products that you can access already. These are based on our L-band UAVSAR airborne instrument. Those are in the NISAR format, and you can peruse those. They're in HDF5 format, so you have to have a reader for that. We also have L and S band data set that flow using an Indian instrument called InSAR. They flew the instrument by a normal plane over to us and integrated it onto our airborne system in this UAV-SAR pod. And we flew 2 campaigns, one in 2019, one in 2021, over California, Alaska, sea ice, and in the East Coast, and created a whole suite of many products that are available also at the DAC. And our geocode is an example of running the InSAR data through the NISAR level 2 processor in ICE3 and producing geocoded products. So these data are available to you if you want them. We also have prioritized low latency. We have fairly relaxed requirements, but our plan is to do things much faster. For level 0, data should be available in 12 hours nominally, and if it's an urgent request, 2 hours. For level 2 products, 6 hours for urgent response. This is something the community really wants, and the project has done their best to minimize the latency, despite there's not really a strong requirement scientifically for it. So that's it. My quick overview. I hope it was informative. If you want to learn more about NISAR, it's probably too late to sign up for the workshop next week, but there is a handbook which is available online. You can find it at the NISAR website, and we look forward very much to a launch in early 2024, where these data will be available to you. Cloud-based tools will be available to you so that you can fully exploit them for your science. So thanks very much for listening. Sorry it took a little longer because of the hiccups we had, but hopefully it doesn't get us too far off track. Questions? You still hear me?
Yep. There were questions about the advantages of using the sweep-SAR method.
Yeah, okay. Were they answered?
I think somewhat. I also understand there's a radiometric advantage, or the SAR image quality is also better, right? Not just the avoiding problems with bursts and burst alignment and things like that.
Yeah, so it's complicated. Whatever argument I make, others might have a counter argument to. For example, Roselle is using ScanSAR and using very sophisticated score techniques to try to recover from the disadvantages of ScanSAR. But normally, to get this wide swath, you have a planar phased array with some sort of a scanning system that allows you to look at different places in the swath and do little snapshots, as Eric described earlier, burst mode processing or burst mode observation. That introduces all kinds of problems. It causes lower resolution in each of the swaths. It causes, as you said, radiometric scalloping, which the TOPS mode they invented to get rid of. And it causes problems of trying to align those bursts exactly in orbit, which the TOPS people, the Sentinel mission team, has solved, but it's non-trivial. For example, SAOCOM cannot align their bursts reliably, and ALOS struggled for a while. So it's all kind of technical issues that require time, money, and effort to try to coordinate. sweep-SAR has its own technical challenges in building this digital beamform system. But once those are all worked out, the operation of it is relatively straightforward, and you can just think of these data as full resolution and wide swath data, where you don't have to worry about the radiometry, you don't have to worry about degraded resolution, you don't have to worry about aligning data perfectly in timing of the observation. So, and to do an equivalent system, and because this reflector is so large, it's 100 square meter reflector. If you wanted a similar kind of capability in a planar phased array, it would have to be of a similar area, and you'd have to have enormous amount of electronics. So the cost of that would be just unbelievably. This is already expensive enough. It'd be very expensive to try to do it with a planar phased array.
Great. Any more questions for Paul?
The disadvantage of the sweep SAR is it generates a lot more raw data that that requires downlinking. So it's another disadvantage, but the final result is higher resolution than what we get with TOPS mode or ScanSAR.
Well, you can always not take as much data.
Yes, that's true.
Doesn't sound like a disadvantage to me.
Yeah. As far as I know, the scientists never have enough data, so I don't think that's a disadvantage.
Oh, it's a disadvantage for the NASA people. They have to pay for downlinking it.
Yeah, so it's certainly a cost driver, but you get what you pay for, and as we say, area coverage rate is really the cost driver in all of these systems. Yeah, so sorry for the hiccup. I'm going to try to go back on my Wi-Fi now, but I don't have to speak. I'm sure it will work.
Shall we take a break until 11:20?
Sounds good.
Yeah.
Sounds good.
Then Yunjun will take the reins and guide us through MintPy, which should be awesome. I'll see you in a few minutes. All right, Yunjun, are you ready?
Yes, do you hear me?
Yes.
Okay. Let me share my screen.
Might want to
Okay,
zoom in.
and zoom in. Looks good, I think.
That's great.
Great. All right, let's start, everyone. So in this session, we will go through the time series analysis using the software called MintPy. It's an open package already available on GitHub. It's the code only does the time series analysis. So the input of it will be a stack of unwrapped interferograms. in either geo or radar coordinate, and then we can estimate the ground displacement time series from it. The MinPy code is most consistent with the stack of interferograms generated with ICE. And it also supports software stacks that is processed with other codes such as Gamma, GMT-SAR, Snap, or ROIPAC. And then you can find the MinPy GitHub here. The detailed algorithms is actually already written in a paper that I published a couple of years ago. And you can go there, check for the detailed, for more explanations if you like, with an example data set and figures already also available in the Jupyter in another set of Jupyter notebooks. So let's first go over this. Please go ahead and then run the first cell. Oh, and also please make sure that you are on the UNAVCO kernel. Then let's just run our first cell. This cell is just going to define a work directory for us. I will just define it as here. And then before we explain more, let's go run a second cell also. This will just download the pre-staged dataset, which is a stack of interferograms that I prepared before the class so that we can use it. Please go ahead. You see it's downloading. After that, we're going to go back and explain a bit more. So you see what it's doing is first, whenever you rerun the notebook, you should always rerun this first cell, which imports all the module to make sure everything else will be run properly. And in this case, the cell here we're running is right now is actually downloading a stack of interferograms prepared already downloaded from ARIA and prepared using ARIA tools that we already practiced before. And this dataset is an ARIA dataset on the San Francisco Bay in California, and it's available on AWS and also on Zenodo if you want to try after the class is over. So you can prepare, you can use these ones that we're downloading right now, or you can actually run these few steps using ARIA tools to prepare it yourself, and then load that like this into MinPy. So we have around 1 more minute for everything to be finished. This is already downloaded and we are decompressed. So we can go below here. There's a question, if we have processed unwrapped interferograms from SNAP, can we directly use it in MinPy? The answer is kind of yes. It is doable. There is a wiki page on MinPy. If we go to the MinPy repository, and then there's a wiki here. Below, there's a SNAP. Here, there's a very brief workflow of recommended workflow for SNAP, and then you should follow this, and then run everything directly into MinPy too. Yes. I will explain a little bit more later words on how we do that, especially in the input part, the differences. So let's first talk about this small baseline app. Small baseline app is basically like the TOPS app or StreetMap app that you have used in ICE2. It's the main workflow, and it basically includes two parts, as is shown in this figure here. The first part is everything done in the interferograms part, where you apply the same operation to all of the interferograms, and then we will do a network inversion to invert for the phase time series, and then everything else later was done all in the time series part. Sorry. Let's see. Okay, so mine is finished. I hope yours is also very close. So this session will basically walk through all these steps as outlined here. And everything that is marked by these dashed boundaries are actually optional steps that you can skip. And then the solid lines are the ones that we usually recommend that is turned on always. And every steps are parameterized with options, and all those options are initiated with a default value in this customized configuration files. And you can leave it as default as you like. You can also use the custom values that you like to change to. So if you go to this link, you will see there's a pretty long configuration file with explanations on what the default auto value is at the very end, and then usually with some explanation on what each of the parameter is and the option is. So for one way for you to get familiar with MinPy software is to basically try to learn and understand more of these full template options. Okay, the straightforward is we're going to check the help message of this script. And then you can see that there's a few options, very generic ones, and then there is a step processing ones, which is also very similar to the TOPS app that we've been using. So this workflow includes these few steps. You can with the start and end, or do step to do each of the single step, or do a chain of steps. Or if you don't specify anything, then we just do everything. And the memory includes these 4 components. First part, we load the stack of the unwrapped interferograms into MinPy. This actually includes the unwrapped phase, the spatial coherence, connected component file, which is a kinetic component file, which is byproduct from phase unwrapping, which is very useful. We will explain more later. The baselines, the instance angles, etc., all those geometry and metadata files, all of them will be loaded into the HDF5 file. After that, we'll do a network inversion to invert the stack of interferograms into a time series. Within the step, we'll do a modified network, apply a common spatial referencing into all of the interferograms to make them consistent in terms of reference. And then we'll do a quick overview to generate some auxiliary files to help us identify the quality of the stack. There's options to correct for the errors from phase unwrapping, and then later words at the end, invert for the time series. Then in the time series domain, you see often they're actually correcting for something. So it's correcting for various source of noises that we observed in the InSAR time series, and then so we can get a cleaned version of the time series, and then we can do velocities and other time functions. The last part will be an output that you can output the MinPy products into other GIS softwares that you like for further on processing. So to configure all the processings, we have mainly 2 types of template or configurations. The first one is a default configuration, which is this file that you already saw before, which is on GitHub here. This file will be this file contains all the configurations, and then they're grouped by steps. And then this file will be copied over every time from the code into your current working directory. And then they will be read every time when the small baseline app runs. There is a second, which is a custom configuration. It's an optional, but recommended. And that's what we're using here today. And the name file name doesn't matter at all, but the inside content matters. And then if you run with this configuration, the code will read the content from this custom configuration and update the default configuration based on it, so that the program will have all the configuration files all the time, but with the custom configurations that you'd like to add. And the next cell is configurations here we added. And the first part is the input of the interferogram stacks that we need. And you can see the first part is the processor. In this case, we're using ARIA, and then you can also specify ICE, the HP3 from ASF, the GMT SAR, SNAP or Gamma or Royal Pack we are still using. In this case, we're using area tools and area products. We specify this, and then later words we specify a reference point. And then by far currently I turn off all the other options so that we can for the teaching purpose. So let's run this, and then you will see it will write the configuration into this TXT file. So by far, we have several questions. This is the first question. What's the input of MinPy? The multiple pairs of infograms produced by TOPS app by default, a stack. Could you answer that in the chat if you like? The question is, we have used the TOPS app, which will generate infograms, and then with the default that we have been using, and then if we run TOPS app multiple times, generate a lot of pairs of infograms, can we call that a stack of infograms that can be directly used into MinPy? Great, thank you. Yes, you're right. So no, they're not, because the default ones generated from TOPS app will be something like this. On the right, they are actually like this, so they're not perfectly aligned. And then what we would like for time series analysis is something that looks like on the left that is perfectly aligned. And on the top here, we also said in this case we're using area, but if you are using anyone else from here, you can check the example of the input files in here. You click a link. This is the documentation website for MinPy. In here, you will see this example directory structures. In this case, we're using area. So these are the area data structures that you will have once you run the area tools. Then the corresponding input files look like this. This is what we're using. But if you are using TOP ICE, such as the top stack, which we'll demonstrate at the end of the day, you will generate a directory structure look like this, and then the corresponding input options for MinPy will be listed here. And you can check that similarly for all the other processors that is currently supported. Okay, so we are clear with input file. Now let's just directly go to the time series analysis. The first step is to the load data. In this case, I actually have already loaded the data into MinPy and then staged it. So you will see that at the very end, it's finished instantly. You don't need to do anything, but let's go over this because I think it's important. Once you run this, you will see that the code read the custom template file we specified here and from here, and then the code will update the default template file based on the input custom. So you basically changed all the autos into the options that we wrote later words. And then it will write everything into these three files. The first one is an infogram stack, which is with a file name look like this. The second one is the geometry file, which includes all the latitude, longitude, height, the instance angle, azimuth angle, water mass, whatever you have. The third one is a lookup table, which is not needed for area tools because this lookup table is used for geocoding. So if your infogram stack is in radar coordinate, you will have that. For geo coordinate, you don't need this. Okay, so the output. The question to Tyler, yes. So the output of this step is in the inputs folder. And you can see in the inputs folder, we have these geometry files and we have the infogram stack. These two are just copied over into the inputs for backup purpose. The idea was that if you generate a lot of infograms from HPC or a big computer workstations, you can run the first step to load the data. Everything will be put into the MinPy inputs, and you can just copy over these inputs to anyone else, and the MinPy can run that smoothly without anything else. And then within this ifgram stack, the H5 file, it includes several sub-data sets as listed here. The most important ones are the unwrapped phase, the spatial coherence, the kinetic component, the perpendicular baseline, and the date format, which includes the reference and secondary date of each of your pairs, and a single flat matrix called a drop ifgram, which is used to flag which interferogram we want to use later words for the analysis. Another file is the geometry, the Geofile. This file includes all the geometries that we will use also. And you can check more here through the link also. This will bring you to the MinPy documentation. This will explain all the data sets, including these definitions. If you scroll up, including the definitions and the comments here also. So besides the small baseline app, there's a few more programs that is very useful in MinPy also. One of them is called the info.py. This is very similar to the GDA info that you have used. If you just run this, it will show the basic file information, or it will tell you the file name. This is a geometry type. It's in geo coordinate with a lot of attributes and then the names and values. So we'll see that this is the Earth radius, the headings, and if you scroll down at the very bottom, it will also show you the data set included in this H5 file, including its shape and its data type. You can run this for every single MinPy files. It will generate a similar thing. And in this case, for the ifgram stack, we have this view we just explained. And we know that you can see here that for this stack, we have over 900 pairs. Each of one is in the size of 1,000 by 1,000 around. And if you want to know the detailed pairs information within this ifgram stack, you can run this minus date option. You can even add a number option. It will list all the reference date and secondary date included in this file and ordered and sorted with a number later words for other usage. I will show you later words. So you can see we have a lot of pairs. And you can check the pairs of information for this interferogram stack using a program called Plot Network. Let's just run this. And then this will basically just give us a basic idea of how the network of this interferogram stack looks like, and then what's the temporal baseline, what's the average coherence level of this stack. And after this program will generate a few plots. Okay, it's already done. So let's just see it. This program will generate these few plots. The first one is a perpendicular baseline history. Base literally tells this, so we know a rough idea of how the variation of your perpendicular baseline is through this time series. And you can see for Sentinel-1, in this case, we have a pretty narrow band, but this is actually not the case for the older satellites such as ERS or MSAT. The baseline is much bigger in terms of usually around several hundreds of meters or 1,000 meter scale. Another is this coherence history, and this coherence history, actually each bar is corresponding to one SAR acquisition, and then each bar here represents the minimum and the maximum coherence for all the interferograms that includes this acquisition. So you will know a good idea of, for every acquisition, what's the worst and the best coherence you can get. And usually if some of the acquisition has, all of them are in very low, both the minimum and maximum coherence are very low, such as this one, or even lower, then we know there's a problem with this acquisition. Then you may want to do something about it, either reprocessing or drop them. The third one is a coherence matrix. The X and Y axis are literally the image number or index of the SAR acquisition. So, and both X and Y axis are the same. So each of the grid represents a pair between the X and Y index. That means here in each grid is each grid is in a field, and then the color of the grid is the average spatial coherence of that infield. And you can see that if we're doing the diagonal, it's the same SRC that is paired together. So we just plot them as a black as a no data, but everything else is a real interferograms pair. And we can see basically that a lot of interferograms, if they are next to the diagonal line, that means they are usually in the small temporal baseline, and they are in a much higher spatial coherence than the interferograms that are further away, which has a longer temporal baseline. And we can see the similar thing in these conventional interferogram network plots, where the x-axis are time, y-axis are the perpendicular baseline. Then each dot is a SAR position. Each line is represent one pair. So, and then again, the color of the line represents the average spatial coherence. Again, you can see here that this short temporal baseline interferograms has usually much higher coherence than the long temporal baseline interferograms. And all these values are actually saved in this file. So you can open that laterwards and then check for all the details that you like. So
John,
now, yeah.
Can you go up to the coherence matrix?
Yeah.
And maybe speak to the bottom half and the top half of this plot and how it may or may not be the same.
Oh, yeah, thank you. That's good. That's a good point. We know that, so this coherence matrix is actually identical, right? From the lower diagonal and then the upper ones, they will not be in the min-pi when we drop some interferograms. So later words, I think many words I will not show, but if we don't do anything, these two will be symmetrical, identical to each other. But in min-pi, if we have that drop F-gram data set, we have the drop. We have this drop F-gram data set, which is used to mark all the interferograms. By default, is all one, so that's all of them will be used. But sometimes we identify some bad interferograms that we don't want to use. We will do a network modification, and then that will turn the specific value within this data set into 0. And then once you do that, then in this plot, you will see some of the lower part of the dots will disappear, while the upper one will still be there. From the differences, you will know very vaguely which part of the interferograms are dropped and excluded from our analysis laterwards.
Yeah, and I'm saying that because I think there was a question earlier this week about, how do I identify bad interferograms and how do I deal with it? So MinPy has this modify network option that would help you identify interferograms that maybe are not good and could be dropped from the network.
Yeah, and it's not written much in most of the paper, but practically it's actually a very important thing that actually can improve your results significantly. Okay, so we know the basic coherence status of our stack of dataset. Then the next step is to check another thing, the masks, which is usually very useful for the analysis. The few masks, there's a few masks. First one is actually first mask is actually the average spatial coherence. Well, we have one spatial coherence for one interferogram, and we can calculate all of them and then do an averaging to get the average spatial coherence to give us a rough idea of how the coherence looks like for this entire stack. And you can see that in this case, everything around this Bay Area is pretty good. This is Sandra's fault. And then so on the west side of Sandra's fault is pretty low coherence. After here is also pretty low coherence. This part is just water, so they're masked out and set to 0.
There was a question in the chat, like what constitutes a good value of coherence? What is low and what is high and what is useful?
Yeah. Oh, okay. So we know coherence are scaled normalized from 0 to 1. Usually because of practical issue, there's a coherence estimation bias. So actually, because of the limitation of our estimator, the code, the algorithm, usually even on the water, if you do process the real data, even on the water, you will see sometimes the coherence will went up to 0.2 or 0.25. It's because we cannot really, in practice, estimate perfect 0 coherence. So in that sense, everything that is usually below a spatial coherence of 0.25 is pretty bad for me. I would usually just don't use anyone below that. Usually, if it's coherence above 0.4, it's actually pretty good. If it's 0.8, it's amazing, which is already, to me, it's perfect. I don't think you really reach to a perfect 0, 1.0. 0.9, 0.8 is already like a perfect coherence. Another mask is a water mask, which is downloaded actually directly from Open Topography here, I think. If you do ICE processing, it will also be downloaded from the SRTM, from the USGS website. Is how it looks like. The last one is what is called the common connected component. In here, I think this is a good chance to show what is kinetic component. Kinetic component is a byproduct generated by phase enveloping algorithms. So after phase enveloping, we will get an unwrapped phase. Then together we will also get a flag matrix, which usually has -1 value, which is the background value, and plus a few other positive values. And these -1 values or 0 values are actually the unwrapping algorithm identified as unreliable pixels, which is so this gives us actually a very useful information of what pixels are unwrapped properly to the first order. So in this case, we loaded all the kinetic component for every interferograms, and then we calculate the pixels that show up as reliable pixels through all the interferograms. This is saved as a file here, and then this gives us basically a pretty good idea of where the good pixels are. Do all unwrapping algorithms generate the kinetic component? No. I believe Snafu that definitely do that. ICU, I think all the other unwrapping algorithms supported in ICE2 does that. The Royal Pack does that. I believe the GMT SAR and Gamma does not do that. Since currently HAPI3 from SF is using Gamma, so it also does not have that. ARIA is using ICE, so it has it. Yeah. And you can see these are the masks. So you can see that it actually matches with our manual interpretation later words after earlier of this average spatial coherence pretty well. That basically most of the high coherent pixels are selected by the unwrapping algorithms as reliable also. Okay, so we know I have a rough idea of the reliable pixels. Now we can do a real analysis, where the first part is actually choose a reference point through all the interferograms, so that all of them will have a consistent spatial reference, because InSAR is interferometry, and in interferometry we can only measure the relative deformation in space. That's why we need a reference point.
There was a question in the chat earlier about what you might want to choose as the characteristics of your reference point.
Yeah, that's a great question. MinPy will choose a reference point automatically, based solely on the average spatial coherence. It will basically just choose randomly a high spatial coherence point, For the processing, if you did not specify anything, but usually we do recommend to manually select a reference point because this part is still, I think, still needs a few more work to make it automatic, which is currently we're not there yet. And the criteria to select a good reference point, basically I have 3 criteria. First, it should be high coherent so that the reference point does not have much decorrelation noise. Second, it should be close to the signal of interest because all the noises that we will show in the next session, especially the troposphere, has a spatially correlated characteristics. That means usually if the 2 objects or 2 pixels are closer, they will have smaller tropospheric errors or noise. So we will want the reference point close, but you cannot really exactly own the signal of interest, right? Then you don't really see the signals. The third is actually also because of troposphere. For example, in the topographic region, such as volcanoes, the troposphere are actually correlated with the topography, and on volcanoes, the volcanic inflation, deflation usually also correlated with topography. So it's a tricky case. Then in this case, based on experience, for example, the papers from Estelle Chartered showed that if you have 2 volcanoes, one is dormant, one is active, and then they're in a similar elevation, then you can choose a reference point in one of the nearby inactive volcanoes. Then you can get actually a better InSAR time series of the active volcano itself. Okay, let's see the running result of this reference point. You'll see that the code is doing pretty fast, actually only 9 seconds. This is because the code is reading this reference point we specified earlier manually, calculate its corresponding row and column, and then it will only update, add these few parameters, metadata into the files without really changing the data value itself, because this file is actually pretty big. But the code will take this metadata into consideration whenever a special reference is needed. So we can see here, again, it's using the info.py script. You can run this script, and you can see now it has this few more metadata added. Now, then we can do the network modification. Then we can do the network inversion. So the invert network step. You can see it's done automatically. There's a lot of runtime message you don't need to worry about. Basically, the code is doing some patching to save the memory to make the whole thing big data friendly. So in this step, the code is basically following the classic SBAS algorithm from Berardino et al. 2002. And also I think David Smith and Roland Bergman also had a paper similarly like that. And they did a lot of work, also published a paper in 2003, which is also very good. It's a similar way. So this step is basically doing that. And then it will invert this network of interference into a time series. And then this estimate time series will also convert the unit of the displacement from the radians, which is the phase unit, into meters, which is the displacement unit, and also flip the sign so that right after these steps, all the time series min pi will be in the unit of meters with positive values of range decrease, pointing positive values after this stage will be representing motions moving towards the satellite. So if it's a vertical motion, then a positive value after this will be uplift. And you can see it's still running. And the output of this step will be a time series, the H5 file, plus a temporal coherence file also, we will see. Okay, still running. Let's see some questions. do we need to consider the deformation rate when choosing the reference point? I don't quite get your question.
I wonder if that's asking if you should pick something where you know the deformation rate, or something that's not the target that you're trying to observe.
Yeah. Go ahead.
I would say, like, I have my what I try to do, which is maybe not what Yunjun would try to do. I would try to pick somewhere where I have a GPS station, if such things are around, so that you actually know what the movement of your reference point is in an absolute sense. Just in case, you know, you see something strange, you want to know that it's not the reference point choice that is driving what you're seeing. But I don't know. Do you have any other thoughts on that?
Yeah, I second that. Or if you are, or if you're only interested in the local deformation, then you know, outside of that area, if there's not much other deformation besides the tectonic ones, which is usually all everywhere, then you can choose a reference point outside of your local interest and then remove a ramp afterwards. After that, then basically the reference point in your signal of interest, then your reference point is basically not moving with respect to your signal of interest.
Right.
That's also fine. Yeah.
So the follow-up question is, do we mean it has to, that they meant that does it have to be a stable point?
Yeah, it actually has, I think it actually should be a stable point. Yeah, exactly. I think that's a golden rule. A stable point means it doesn't change, right? It either has a known deformation rate or deformation where you know already, and then or does not have.
Yeah, even if it's far away, I mean, it has to be within the scene, right?
Yeah.
Yeah, something that is within your data set that has a motion that you would expect to be predictable or stable. And there's another question about parallelization.
The parallelization, we will not talk about this in here, demonstrating this, but actually, I think you're talking about the entire thing, right? Not just MinPy. Let's do one by one. In MinPy, there are parallelization to some extent, not entirely. We do actually parallel the two most time-consuming steps using Dask. So let's go to Google. If you search MinPy GitHub, we'll go to the GitHub repository. And in here, there's a documentation website. And in here, then on the left, you will see this parallel processing. So this is a work done by David Grossman and another student, I think with last name Zahner from University of Miami to our undergrad, which is very impressive. They added the Dask support for parallelization in MinPy. And then what you would do eventually, super easy. You just, there are two MinPy options right here. You can actually just change the value from auto to local, and then specify a number of workers. Then we run the small baseline app. Then you will do the parameterization automatically for you, which is super easy to use. And I actually use that all the time. And these are the performance that they provide, they evaluated. The y-axis are the runtime of one single step, which is a networking, which is the invert network step. The x-axis are actually the number of CPUs. You will see that with these are a relatively realistic size of data set. You can see with more CPUs, you get a significantly less runtime. In this case, this is a very, very small data set. When you have more CPUs, you actually spend slightly more time on I/O than computing. So in this case, that's not really help that much. But most of the case, we're actually following the right plot. Okay, now we finished this step, and it will generate InSAR. I will generate a time series H5, and we can use import PY to see the structure of it. You will see that it has a few metadata not often listed, but in the data set, we have a time series with a 3D shape, where the first part is the number of acquisitions we have, and we also get a perpendicular baseline time series and the date. And we can plot this using another script in MinPy called view the PY. This will be your best friend. Study and use it. You will love it. You will realize once you know how to use view the PY, then you will see all these H5 are not a mystery at all. So you'll see it plots everything. We have these many data sets, and it's still plotting. Okay, this is the result of our time series. And you can see it's by default, choose the first date as a reference date, and then everything else is with respect to this. And we can see very clearly more and more the interseismic deformation around this region, especially through the later years. So that's basically the first biggest part. And here is a question to you all. Why do we go through all these network stuff? Why do we invert a network of small baseline interferograms to estimate a single reference time series instead of forming directly a single referenced network of interferograms at the first place? Let's see the chat. Let's see your answers on the chat. Good answers. So I would say, yeah, I like the Alex answer the most, because if you recall from Heresh's presentation on Wednesday about the time series theory, remember the coherence level of interferograms is usually also depends on the temporal baseline because of the temporal decorrelation. So we use small baseline. To minimize the decorrelation or maintain the high coherence as much as possible, so that we can have a coherent long time series. And of course, when we do a network like above, we have a lot of redundancy. That redundancy also helps to minimize the random decorrelation noise also. And everything, of course, then is the goal to have more points. But in this case, I don't think the deformation either is linear or nonlinear. In this case, I think it's all fine. Okay, so now we have the time series for a lot of people. If you're interested on substance, volcano deformation, especially tectonic studies, you will want to know the velocity instead of the displacement time series. So in this case, we can invert the time series into velocity just by fitting. In this case, we're just fitting a linear slope through the entire time series for every single pixel independently. And then this will generate a file called velocity.py, velocity.h5. And above, I actually just renamed them to raw for a comparison purpose laterwards. So now let's just plot the velocity by running this cell. And these are our result. Let me zoom out a little bit so that we can see the full scale. Yeah, so these are the result. And if you hover around, I believe you could see the value. Yeah, if you hover around, you can see the value at the bottom. of the pixels. And then we know again, in this case, these are our reference point. This is still at the Bay Area. And then we know the negative values, as shown in the blue here, are the motions that is moving away from satellite, and then the positive are moving towards satellite. Yeah. And then there's a few obvious features. The first features that we can see is this general from blue to green to orange patterns. These are actually the tectonic deformation, because this is Sandra's fault. So on this side is the North American plate. On this side is the Pacific plate, and then they are moving with respect to each other with these with the structural faults. Is there an artifacts northwest of the Hayward fault? You are talking about here, right? Great catch. Yes, as an artifact, and we'll talk about that in the next session. Great catch.
Somebody must have fed you that question. That like cues up Hyunjun perfectly for what he's going to talk about later. Great question.
Great question. Yeah. And then we have the Sandra's fault here. We have the Hayward fault here. We have the, what's the name called? This one.
Which one? What are you pointing at?
This one here.
It's the Concord fault.
Concord fault. Thank you. Yeah. So we have, you can see we have many faults here with values. For example, we can see here from this near the reference point, we can see the value is almost 0. These are the velocity. V is for velocity, and it's in the unit of meters per year. So in this case, this is centimeter per year. Sorry. So the V is actually almost close to 0. Where you can see the blue here is already 3 millimeters, while in here is half a centimeter already. So you can see the value. And another part, yeah, and another part of feature is right here. Actually, this is another fault called what? Called Silver
Creek.
Thank you. Yeah, Silver Creek fault, and then this whole part is a region in Santa Clara. There's a big water aquifer here, and then we will later on see the very interesting and complex deformation time series of this aquifer. Yeah, and then if you want to know more, you can know the fault database from the USGS. I click the link here. And okay, before we go into later words, in this velocity, the H5 file, besides a velocity, there's another data set called a velocity standard deviation. These are literally the fitting residual of the time series of the slope linear regression. This can basically tell us how good the linear velocity fits the time series. And you can see partly here, again, this is the reference point. Near the reference point is almost perfectly 0. And as we go further away, we can see the standard deviation is getting slightly bigger and bigger. This also matches our understanding that the residual, especially the tropospheric delay, is a spatially correlated feature. So when you are moving away from your reference point, you get a slightly bigger uncertainty also. In this case, this is the aquifer from Santa Clara. And then this part is actually because this linear line that we're fitting is actually not suitable, because here there's more complicated deformation that a linear line cannot describe. So that we result in a slightly bigger uncertainty here also.
Can you, Hyunjun, just scroll up a little bit so that I can see the title? No, just the figure with the figure title. Sorry, I'm taking screenshots for.
Oh, sure.
You too, huh?
Okay, so our last question before we end the session is, what do you think? These are basically kind of one ways of the uncertainty of our InSAR velocities. What can you think of the source of the errors that we have learned through this class so far that could potentially be the that could potentially contributing to this uncertainty in terms of in terms of the physical processes or names or sources of basically the sources, basically the source of errors in InSAR. Let's see your answers in chat. Ionosphere, yes, for sure. Ionosphere, troposphere, yes. Nonlinear deformation rate, great, yes. Unwrapping, I guess you mean unwrapping errors, yes. Low coherence and decorrelation to some extent, because in here we masked actually based on the temporal coherence, and then with high temporal coherence, we're trying to eliminate the decorrelation noise pixels with high decorrelation noise. So in this case, everything showed up is actually pretty high coherent, so the decorrelation noise effect will be much less. Okay, great. I guess that's it. So basically, you will see, basically as you can see already, the input of MinPy is a stack of interferograms, and the output will be a velocity and a time series, and they look like this. And there are more geodetic or geophysical part laterwards, but we will continue after taking a break. And let's see if you have questions. SBAS uses combination NC2, mean number of connection 2 approach to provide multiple possible time series. I don't get what you mean. If you want, please feel free to unmute and speak also.
Hi. So actually, I want to say that while working in PSNSAR and SBAS, so PSNSAR is basically for which if we have n number of images, so we can provide n minus one number of interferograms. But when we use this model approach for SBAS, it uses like 2 interferogram combinations, and it provides the NC2 number of interferograms. So in that cases, the spatial decorrelation over the PSNSAR is quite different from the spatial correlation in SBAS. So is that like what exactly the advantages, and it adds the error into the spatial decorrelation principle?
Thank you. That's a good question. So let's say in PS, or if we only have without any redundancy, we only have n-1 interferograms, which is literally this one, right? We would have a one pair, which is a black line here, and we connect them directly. And then your question is, what if we have the redundancy, and they would mix up the high coherent ones with the low coherent ones? Will that mess up our results? I assume, right? If I understand it.
Yeah, you're right.
Okay, great. So it won't, because that's how we do the SBAS. When we do the SBAS, we can either wait. You will later on see there's options to do the wait when we have the redundancy for the single part of a time gap of a time separation. By waiting, we can probably discard the low coherent measurements. They will have less impact. And also by doing the masking, when there's option to mask low coherent pixels for every single interferogram based on spatial coherence, that will also minimize that. But even if we don't do any of this by default, just without waiting, without masking, on average, they will not also make it worse because of how the least square estimation works. Of course, I believe, if I remember right, is if you do that, the final result in terms of the decorrelation or coherence will be like slightly worse than your best possible single interferograms, but it's pretty close. but it's very far away instead from the bad coherent infograms, actually. I hope this answers the question. Module not found. Are you talking about issue value? Are you talking about this one? This cell? Okay, great. Let's see if there's more questions. Okay, then shall we take a break?
Sounds great. How long do you want?
So how about we resume at 30 minutes, 12 minutes?
12:30?
Yeah, 12:30.
Sounds good.
Okay. See you.
Ready?
Yeah. So let's start. So in this second session, we'll talk about a lot of really interesting things, the area analysis, which is really my favorite. So in InSAR part, we'll talk about what is signal and what is noise. It's because it's really subjective. Very popular words. Your noise is my signal, or my noise is your signal. And we have learned so far there's a lot of InSAR noise sources. And in here, in terms of time series analysis, we can actually group them into two types. One is on the green, one is on the blue. The green ones are including the deformation that we're interested in, including the atmosphere, such as troposphere and ionosphere. There's geometry, which includes the topographic residual from the DM errors or the orbital errors. And in case of MSAT, there's this local oscillator drift, basically a clock in the MSAT satellite, which is shifting. And there's tidal forces, such as the solid earth tide, the ocean tidal loading, pole tide, which is much smaller because of the gravity pull between the Earth, Sun, and the Moon. And then there are secondary loading effects. And then there is the last part, which is the blue one, the second type, which I categorized them as the non-closure phase contributions, which means these phase contributions, when they form a phase triplet of ij plus jk minus ik, which are later words, that they're not equal to 0. And these error sources, including the random decorrelation noise, the potential phase unwrapping errors, the processing inconsistencies due to the filtering and multi-looking we applied during the processing, which is actually very small, so we can neglect that. And the last part, which is the most interesting part, is actually the non-closure phase due to the short temporal baseline interferograms, which has been really a hot topic in the recent 2 years. We'll talk about this also later words. So in MinPy, before the network inversion, we think all the green part are signals because they form the strict closure phase, so they can be all inverted or estimated together into the time series part because they'll be exactly the same either in interferograms or in time series. And since interferograms are much bigger, so we try to save them into a time series, then we can correct them afterwards. That's just much simpler and also much more efficient. And then after that, after the network inversion, we can start to isolate or separate these other sources from the deformation so that we can get a better estimate. And then first, let's then talk about the quality of the inversion, which is an estimation of all the green parts. And in this part, again, the noise basically comes from the blue, right? Which is basically these few parts. The first part, decorrelation, and that is why we use SBAS, use a small baseline to mitigate the decorrelation and the unwrapping errors. So for this part, there's a few good quality measures that can be used that can help us to evaluate the quality of the inversion. And two of them, very obviously, one is the average spatial coherence, which we already showed earlier. And another one is the temporal coherence. The temporal coherence is a byproduct in the inverted network step. It's actually literally calculated as this equation, which is actually very simple. The delta phi, or the unwrapped interferograms, the unwrapped phase. The phi hat is the estimated InSAR time series phase, and A is a design matrix. And by A plus this phi hat, we can reconstruct the stack of interferograms from the estimated time series, and then compare that with the input observed interferograms, and then do an averaging. So this temporal coherence is literally showing how good the fit of our network inversion is. And again, also it's normalized, so the value also varies from 0 to 1. And by default, in the code, threshold of 0.7 is used, which means basically all the things that we show later words by default, all the pixels with a temporal coherence of less than 0.1, less than 0.7 are already masked out and not shown here. And now we can plot these two files again to see how they exactly look like. This is the one we already see before, and these are the temporal coherence calculated from the SBAS inversion. Again, this is the reference point, and we can see the two of them, they are actually pretty similar, except earlier, as some of you has already noticed, they are in the velocities, there's an artifacts, right? And we can see actually these artifacts clearly in the temporal coherence as well. So we will later on try to figure out why. And okay, so this comes to a question. I think it's a good question. We know this temporal coherence, the equation here, you can see on your own screen, the definition. What would be the case, what would be the temporal coherence looks like if we only have a single referenced interferogram stack? If there's no redundancy in the input interferogram stack, and then we invert for InSAR time series, and then calculate the temporal coherence, what would be the value of the temporal coherence looks like? Let's see your answer in the chat. Because when we do the S-bus inversion, we are actually taking the redundancies of the interferograms, of multiple interferograms that is covering the same time period, and we're somehow doing the optimization to get the estimate. And if we don't have that redundancy, then the S-bus inversion result, what will it look like? It should be exactly the same or exactly equivalent as the input interferograms if there's no redundancy, right? So it would be literally zero. Sorry, it would literally be 1 everywhere, because in that case, if there's no redundancy in the delta phi, these two delta phi hat and delta phi will be identical to each other, and then this equation calculation will be 1 everywhere. Sorry, including these low coherent areas, it will also be 1. Water is maxed out, so we don't count that, but everywhere will be 1 if there's no redundancy. Then in this case, the temporal coherence will not be useful at all. So basically the take-home messages is we want our interferogram stack to be redundant so that we can have a meaningful value of the temporal coherence. So the second question is, we see this spatial coherence and temporal coherence. We see these two maps are pretty similar to each other, but there are some differences, such as this one here. Why are they different? What's the cause of these differences? Please type your answers in the chat. Again, these two, the hint is both of them, they are actually the parameters for the inversion quality. And we know the inversion quality are controlled or depends on the noise of the inversion, right? So basically is both of them will be affected by the noise of the network inversion. And the noises are we listed on the top. All the things that are blue are the noises that will change the temporal coherence and average spatial coherence. But the question is, those two are different. Especially here, there's a line, there's artifacts, and this artifact is caused by what? The answer is basically among these 4, right? What would be your pick? Please type your answer in the chat. Based on your understanding of how the temporal coherence and spatial coherence are calculated. Let's wait for a few more answers. More guess? So all these answers will contribute to the imperfect coherence that we see in both the average spatial coherence and temporal coherence. But actually in the average spatial coherence, there is no unwrapping, right? The average spatial coherence are actually estimated from the wrapped phase. And so that means the average spatial coherence actually does not account for the phase unwrapping and its potential unwrapping errors. So that is why, so this is the correct answer. And that gives us a really good thing is that basically we can, in reality, just compare those two. And if you see there, even if you see these artifacts like this, then you will know there's phase unwrapping errors in your data set. That means you want to go back and check it. And in this case, we do have. And this artifacts is like with this kind of a geometry. This does look like matches with the frame boundary of the SAR imaging. And so we know that this could potentially actually be the phase unwrapping error due to the imperfect stitching. The phase stitching we apply when we are running array tools. So the next step is, okay, we now know a rough idea of these potential unwrapping errors. How can we do a more strict or more accurate detection of the unwrapping errors? One of them is actually just using the closure phase. And in this case, again, we know the unwrapping is literally adding the integer number of 2 pi into a wrapped phase to form the continuous unwrapped phase. So if there's an unwrapping error, that unwrapping error would be literally an integer number of 2 pi. And first, by looking at temporal coherence, we could have a rough idea of where the unwrapping error is, but there's a more accurate way. Let's first see how the unwrapping error looks like by running this cell. This cell is again using the build.py script, and you can see it print out. You can run in command line, later words in terminal if you like. You can run the build.py like this, and then it will show up. This basically plots all the unwrapped phase with a reference date as this, plus a random secondary date. And as you can see here, so you can see very clearly among these few interferograms, these two are having unwrapping errors with this clear jump, since our reference point is here. And of course, if you put a reference point around here, then this part will have unwrapping errors relatively. And based on the geometry, we know that this should be because of the imperfect stitching when we're preparing the array products. And literally you can do that in practice to check every single interferogram that you have, but it's just very impractical because we have a lot of interferograms. In this case, we have close to 1,000. So you may not want to do that. So one way is to calculate this, what I call this non-zero integer ambiguity of the closure phase. Again, the closure phase is defined as this. We have an interferogram formed by acquisition ij, jk, then minus the ik. We can calculate the closure phase of an interferogram triplet. Then we can calculate the integer part of it. And we can see that if the integer part is not equals to 0, then there's an unwrapping error there. And we can count that for all the interferogram triplet through the entire stack, and then count the numbers. So which is the t int here. And we can do that in this step. Please run the cell, and we can see how it goes. So this step is literally calculating this t int value, and we can see the t int value, and we can see from the equation here is basically saying that if this integer part of the closure phase is not equals to 0, then there's unwrapping errors, and we can count that. That means for every, and this is calculated independently for every pixels. So that means actually that for every pixel, for each pixel, if this t int value is equal to 0, that means this pixel has no phase unwrapping errors in any interferograms. And if it maxed out, then it has unwrapping errors in all interferograms, right? So we can see the calculation and the plotting here. This is how the t int looks like. And then the value is here, and you can see this part is the histogram of this 2D matrix. And we can see here, basically, this is a reference point. Everything incoherently connected to the reference point has almost close to 0 value, which is very good, which means there's not much unwrapping errors. And you can see, go to these mountain regions and go to here, there's values close to 400 or 800. That means there's a lot of unwrapping errors. And you can see, especially on this right peak, that this non-zero peak, note that this is in log scale. So the difference from here to here is actually huge, significantly. So we only need to care about these peak values. And you can see this peak value is actually non-zero, very close, but not exactly. And this peak value is there's a lot of interference, like around 100, that has non-zero integer ambiguity, and it has a lot of pixels. And in this part, we can visually connect this to these regions, right? These regions are having errors, and the t in the value is around 100. So this map is really useful. Basically, again, the take-home message is if the pixel has a t in the value larger than 0, it has errors. And especially in this case, if these areas having exactly the same t in the value, it means actually it shares the same phase errors, which is also relatively good news because we can correct for it, right? And in this part, this value, these errors are actually pretty random and chaotic. That means we can actually not correct for them. We just have to leave it behind. So the question now comes is, after the time series analysis, which metric better represents the quality of the inversions? A, the average spatial coherence, B, the temporal coherence, C, the common mask from all the kinetic components, and D, the water mask. Please type your answer in the chat. Excellent. Seems like we're all on the same page. Great. Okay, so now we know where the phase error is, which is here, how we can correct them. In MinPy, there's 3 methods to do that. One part is bridging, which is really a historic method by literally constructing a bridge between these 2 areas and force a smooth connection between the 2. And by, for example, in this area, by adding an integer number of 2 pi into this region of the phase, and then make sure these 2 are smooth across the boundary, like bridging. And then this MinPy can do that in an automatic way based on the kinetic component generated by, for example, Snafu. The second method is using the phase closure. This method is a time domain method, but again, by literally, we know this t-int should be 0, but it's not. So the code is writing an equation and solving an equation to make sure to enforce this part to be perfectly 0. And by solving that, you can somehow estimate the unwrapping error in time domain for each pixel. And the third algorithm is just combine the 2. You apply bridge first, and then apply phase closure after that. Sometimes this gives us best result, sometimes does not. This algorithm sometimes works, but it's not working. But it's not working all the time. So use and judge based on a data set. And that is also why I usually don't turn it on by default unless you know there's an error and then you want to correct for it. In this case, we know, so we add this into our template and run this step. And you can see the code is reading this option from the custom template and then modify it and then modify the default template. After that, the bridging is done in the pair or interferogram by interferogram basis. Literally, for every single interferogram, we have that kinetic component. We are detecting the offset between different kinetic component and adding a smooth constraint. Let's see if you have any questions, but this will take a while. 3 minutes.
There was a question earlier about changing reference points and what it would do to your results.
Yeah, changing reference point. It affects everything. InSAR is relative again. InSAR is actually a double difference measurement. It's actually relative both in time and in space. And on the space, the reference point is the reference. So everything you measure are with respect to that reference. That's why we want to keep it close to your signal of interest. And even, for example, in our earlier case, in here, our reference point is here. So that's why in this region, with respect these pixels, with respect to this reference point, there's no RMP error. But these ones are. And if we move our reference point to here, for example, then you will see that this part has no RMP error relatively, while this part will have a lot of RMP errors. So reference point is actually really important, and then that is why we recommend choose that manually based on your knowledge of the study area. Tyler asks, so once you know this, do you throw out the entire interferogram that has RMP errors? Yes, that is actually one way. You can actually, in here, we're trying to correct them because we know this RMP error pretty well, and the method works with this type of RMP errors, so we correct them. But in some case, for example, if this region, for example, interference crossing Himalaya, Eric has a lot of experience with that. In those cases, once you're crossing those kind of challenging areas, the RMP errors are not as regular or as artificial like this. Then the RMP errors sometimes not really work. In those cases, you will just want to identify them and then drop them. You can do that in the step called the modified network. Again, so we'll show it here. Okay, we can actually show it here, and then since I will not run this. You can literally identify those interferograms and then drop them, and then rerun the network inversion. So make sure that your time series will not be affected by those interferograms. So that is basically, to me, that is one of the big reasons to do the network inversion. To do the network modification is another bigger reason to do the network modification is to drop the low coherent interferograms. If some interferograms, or for some reasons, because of long temporal baseline or spatial baseline, has really overall very low coherence, then you may just want to ignore it. And this is one of the examples of how that improves. This is actually an interferogram stack from ALOS on Galapagos Island or volcanoes. This is actually the Sierra Negra volcano. This part is the caldera, and you can see, again, this is the network plot. The color here shows the average spatial coherence of each of the pair of the interferograms. And you can see that some of the pairs, when they have both a long temporal baseline and a big perpendicular baseline, it has low coherence. In this case, I just use the network modification by calculating the average coherence, which is identified as the blue square here, and then calculate the temporal coherence, calculate the average spatial coherence for each interferogram, and then just using threshold to drop all those red lines, the corresponding interferograms, then went into a network look like D, and then we can rerun the inversion. We can get a temporal coherence look like this. And you can see that the temporal coherence on the crater, on the caldera, and on the forest here got significantly improved. The takeaway actually for this is this kind of network modification solely based on the average spatial coherence actually works the best if you can manually choosing an area of interest to calculate this value, and this area of interest, this bounding box should be an area that covers your signal of interest. Then the whole value here representative will be much more representative to your signal of interest.
Are you considering a feature where you might allow you to have a polygon that's not a rectangle? Because for the Bay Area, you probably don't want to include the Bay.
Yeah, you can. It's just not as convenient as it's just not convenient as a bounding box. You can specify. I don't put the options here. You can check the link. These are all the template options related with network modification. You can see there's a lot. For example, for what Garrett just said, you can actually specify a mask file, where the mask file can be very random, of course. You can, and then the code will calculate the average coherence solely based on the mask file, and then the polygon works well.
Oh, that's cool. I have to try
Yeah.
that.
Okay, so the breaking is done. And we can see the result. It's here. I'm plotting the unwrapped phase before the correction. Unwrapped phase after the correction, the data set has a bridging surface and the corresponding kinetic component. So you can see that the code is literally using these two and then trying to connect to the phase marked by the blue and the red areas. And you can see the unwrapping area is gone. And I'm expecting basically the same effects for all the interference that has unwrapping errors. And with this, we correct for the unwrapping error. Then we need to rerun the inversion to get the corrected InSAR time series. Later words. Now we have covered this. And then for the network inversion, we're also already covered. Then we can see that actually the network inversion part itself. One of the new things in MinPy added to the classic SBAS is the weighting. You can weight the inversion based on several different parameters. The default one actually is using the inverse of the covariance as the weight, which is actually theoretically also in simulations the best ones that we have. You can actually also using other parameters such as the feature information matrix or coherence directly, or as we used in our case, no weighting at all. The last one is for offsets, which is not needed in our case here. And another option we mentioned earlier also is to do masking. Because by far, we are estimating, we assume every pixel in this case by far has valid unwrapped phase in all interferograms. But if you want to do a masking, for example, based on the spatial coherence, because every pixel at every interferogram has a spatial coherence value, and I can use that as a weighting by removing those pixels with low coherence from the inversion. And if you do that, tricky thing is in this case, every pixel will not have valid unwrapped phase in all interferograms. And in this case, MinPy is handling that automatically, and then in this case, the resulting temporal coherence will also has less number of observations input, which is very similar in the case, very similar to decreasing your redundancy. And then so in this case also, I would, if I turn the masking on, I would usually raise the threshold of temporal coherence to make sure my results are reliable. Last part is actually if people are interested in the technical details, there's optimization methods. One of them is using the phase, one of them is using the phase velocity. Both of them are originated from the Berardino's paper, and MinPy has both of them. And by default is using the later one because it's physically a better solution, a more robust solution. But if you want to use the other one, you can do that with this option also. Okay, so with all this, you can try to turn this on in your own playing. In this case, we will not for the time consideration. So now we have correct for the phase RP error. So we'll just do the network inversion again. And yeah. And one of the few key parameters of the inversion is here. It's saying that we're using the least square with L2 known. We are having a minimum constraint of the redundancy for every single acquisition. We need to have at least one interferer that is covering each acquisition. We're not doing any weighting. You can turn that on. We're not calculating the covariance, which is a currently experimental feature. We're not applying the masking. And so the goal is to check the temporal coherence, how it looks like before. Now is after we correct for those phase RP errors. This is old text. Let's see if there's any questions.
I didn't see any.
Okay. As you can see, this part actually takes, it's still pretty fast, but takes the longest time. And then if you turn on the weighting will apply this inversion pixel by pixel, which will be much longer. And that is where the case, the parallelization will help a lot. So in practice, I personally turn on the parallelization all the time. Okay, we're done with the onion. Let's see the, sorry for scrolling. Let's see the result. Voila. The temporal coherence, the new one, we don't see these artifacts anymore, which is a good sign. Basically means there's not much RP errors left. So the question, for example, you can see that in this region we used to have RP errors, and now we don't have it anymore. But you can see this island, these few islands here, the temporal coherence, they're pretty low, and very obviously they're crossing water, so there are RP errors here. But if your signal of interest is in one of the island, what will you do? Please type your answers in the chat.
They're not all islands. Some of them are like the Marin headlands. They're just cut off by the edge of the frame.
Right, that's part. Yeah.
Yeah, the Golden Gate Bridge connects to one of them.
Yeah, I think you all get it. That's right. Exactly. Put the reference point in one of the islands that you're interested in. Okay. So now it looks like we got a pretty reliable, confident that a good InSAR coherence, InSAR time series with good temporal coherence. And now, so that basically free us from the impact of the decorrelation noise. Now, if we go back to see the noise we have, we're basically now pretty fine with the blue parts. And now we have all these included. And if we are only interested in deformation, we want to remove all this. And we can do that in the time series domain. And that is what we're doing here. And there's several of those. And there are several of those sources. They're all pretty physical. The atmosphere, the tidal effects, the geometry effects. The first one is the troposphere that you already now should be very familiar with. And the MinPy supports 3 types of methods. One is using the global atmospheric models, using the PyAPS software developed by Roman Jolivet et al. From Caltech originally. The other is the Gecko's corrections from Newcastle originally. And the third one is actually an empirical method using the empirical relationship between the stratified troposphere and the topography. Two of them, if you plot them on a scatter plot, you'll see that a lot of times they will have a relatively linear relationship. And then you can, this method, estimate this linear slope and then remove that from the InSAR. But of course, this assumption is pretty strong, so you should be cautious. And this method, I usually use this method, the PyAPS with the ERA5, a weather reanalysis model. But in some case, when the model is not good, this method, the empirical one, actually sometimes in the string topography will outperforms the PyAPS method. But this is still an active area of research, so I would really play with them and then check them manually to see which method works for you the best. And then they can be turned on very easily using template option. It will look like this. You can specify one of them. And then the output of this step will be an ERA5.h5 file, which is the estimated tropospheric delay using PyAPS. And the code will literally calculate the differences between your time series H5 file and the ERA5 H5 file, and then save the differences into a new file look like this. And yeah, so that's basically that. Note that the ERA5 file is weather products is actually distributed independently from the Copernicus surface. And to really use it, you need to have another account registration, and you need to also agree on the terms. And all of them can be found in the PyAPS website. You can copy paste this link here. And then in here, you will see there's besides installation, there's account setup. Please try this, and then you actually have to try this, all of them, to make sure the account is set up correctly. Especially make sure that you accept the data license and the terms of use, and then you can test your data downloading through this. And this will be in one of our homework, because you will need that for sure later when you do your own processing. The second correction is a solid Earth tide. Again, this is the gravity pull between the moon, sun, and the Earth, mainly actually from the moon. And then this solid Earth tide is actually already very well studied 50 years ago, and now it's already a standard survey. There's a standard convention called IERS, and MinPy use another package called PySolid that implements these conventions and already integrated. So what all you need to do is turn this on to do the correction. And this actually works the most for large area analysis. Like, for example, if you're crossing California, crossing Tibet, or the half of Turkey, then this solid Earth tide will introduce a very long spatial wavelength component in your velocity field or in your time series. And then, yeah, but for the small areas, it's not really that important. Another part, which is recently actually a new thing, is identified by the colleagues from Caltech, Ollie Stephenson and Yuan-Kai Liu. Both of them, they are PhD students. They found that the bulk motion, the rigid motion of the tectonic plate, which can be up to several centimeters per year, can actually introduce a long spatial wavelength gradient in your velocity field in the magnitude of millimeter per year level, crossing several hundreds of kilometer scales. Because this bulk plate motion, when you project that into a line of sight with a range-dependent incidence angle, will introduce a ramp, which makes sense, right? And this ramp is shown here. For example, this is one case in Iran. It's part of the Eurasia plate, has a plate motion like this. And then when you projected that into the range-dependent line of sight, it will introduce scale, which is actually very small. As you can see in this case, is actually less than 1 centimeter per year across the entire Sentinel-1 stack, across entire Sentinel-1 frame. So also basically means these plate motion effects is only affects the large scale analysis. And if you are only focusing on a small city scale or volcano scale or land substance, then you don't really care. But if you're working on interseismic, it's actually pretty important. And this one, Kai has implemented the MinPy as a script called backplate motion. It's not integrated into the small baseline app yet, but we will soon. Another part is the non-closure phase that we mentioned briefly. In recent years, there's a few studies actually from DOR, especially this one from Homa Ansari. They find that when you use the small temporal baseline interferograms, the resulting S-bars result will have a biased displacement time series and velocities. And this biased estimation has been confirmed by several other groups and studies and has been linked to this non-zero closure phase. And when we talk about this non-zero closure phase, it's similar to the above, the phase hopping error part, but it is the non-integer part. We have this closure phase look like this, and this closure phase will have an integer part and a non-integer part, and they find that this non-integer part can actually lead to a bias in our S-bars result. And Zheng Yujie et al., a group from Kinetic and JPL, has developed a simple mathematical model that explains both the non-zero closure phase and the observed systematic bias, and shown that this non-zero closure phase bias is actually an indicator of a temporally inconsistent physical processes that alters both the phase and amplitude of the interferometric measurement. I know it's complicated. Don't worry. The paper is there, the code is there, so the model and the algorithm from Yujie's paper has been implemented into MinPy since the recent release as another new script. And the figure below shows the exact impact. This is a study area from Yujie's paper where she chose the Southern California. These few blue areas are the dry lake. And bottom here is actually San Andreas Fault with the Salton Sea around here. This is the area with Sentinel-1. And with Sentinel-1, if she runs the small baseline app with a bandwidth of 1 connection or the nearest connection, then she results InSAR velocity look like this. But if she uses a bandwidth of 5, means interferogram stack with connection 1, 2, 3, 4, 5, then she will have a slightly different velocity estimate. And if she uses 10 with another different one. And the method she developed can estimate these bias, and then the estimated bias velocities are shown in the central row. And if we do a difference between the top and the central one, you get the bottom one, which is the bias corrected InSAR velocity. And now you can see across in different bandwidths, the corrected velocity are consistent with each other. So there's already, Yujie has already wrote the code and a Jupyter notebook to demonstrate the usage of this script. And then the Jupyter notebook, which is relatively long, is all available on GitHub. You can click the link here. There's a MinPy tutorial repository independent of the code repository. It has a detailed explanation of how the code works and what you should do and how to interpret the results. And in this case, in this class, we will only demonstrate the detection of the potential non-closure phase bias using a parameter Yujie called the average sequential closure phase. Again, this closure phase, C and K, is defined like this. Well, K is the number. So let me define this again first. C, this is the one when we call the sequential closure phase, which means that the closure phase can form beyond triplets. You can form a closure phase by using interferogram 1, 2, 2, 3, 3, 4, 4, 5, and minus 1, 5. You can get a closure phase with a longer temporal spline, and we call that this C51, which is the connection level 5 closure phase starting at acquisition 1. And then you can see, of course, then you can start at number 2, then acquisition 3, and forward. And then what you can do is then you can do an averaging of all the sequential closure phase with the same connection number, and we call that this average sequential closure phase at connection level n. And by calculating this, she found this is a good indicator of the potential non-closure phase, and we can do that using this script. And let's just run it. And in here, we're only generating a mask, and the connection level 28 is because if we go back, check our network of the stack, you will see from the coherence plot, you will see these are our network stack. Then this black line are connection 0. Next to it is connection 1, and you can see actually if you zoom in, we have connection for this interferogram stack, connection up to number 3. Plus this annual pairs, and this annual pairs has a connection actually up to 28, which is a crossing from acquisition here all the way to here. So that's why in this case, I use 28. If you process your own interferogram, for example, if you process your own interferogram stack with a connection 1, 2, 3, plus 5 or 10, then you may want to choose, in this case, when you do a calculation here, you will want to choose your connection level up to 10, which is the connection level of the temporal baseline that the model assumes they are bias-free, because these bias are assumed and observed to be only affecting small baseline interferograms. If you have a long temporal baseline interferograms, they are fine. Let me know if you have questions for this. Sorry for scrolling. Okay, so this calculation is done. Let's plot the result. This calculation is generating these two files. One is average special, one is average sequential closure phase. One is the mask generated from it. And we can see the two of them look like this. Because this average sequential closure phase is a complex value with the amplitude normalized and with a phase. So when the amplitude is big enough, it means it's actually coherent. If it is coherent and it has large enough phase, which usually means these are the regions that have potentially has non-zero closure phase and coherent, which will be remained in our InSAR processing and bias our interpretation. So in this case, by adding a threshold on both the amplitude and phase, we can identify regions as shown here on the white pixels, the pixels that could potentially be affected or biased by this non-closure phase. And through a calculation, through accounting, which I did not show the code here, this region, the white region, is actually around 20 pixels of all pixels on line. Or if you only count the reliable pixels, which are pixels with high temporal coherence value, then 20% of pixels that could actually be exposed or potentially has this non-closure phase bias, which is actually a significant value. So that's why that's why it's here. And the primary affected region one is here. This is the San Bruno Mountain Park on the south of San Francisco, and in this region, which is a few left good pixels on the west side of San Andreas Fault. So yeah, so this is that, and then you can check the notebook for more detailed instruction on how to estimate this bias and then remove that from your InSAR analysis. I will stop here in case you have questions. This is really currently the state of the art and the very active region of research.
Could you maybe say talk a bit more about the circumstances in which you might expect to have to apply this correction? It's more important in some places than others, right?
Yeah, that's a good point. Thank you. So this correction is really based on a model from UGA, is really indicating areas with temporally inconsistent physical processes, such as, for example, the farmland with soil moisture changes very rapidly, or actually desert from Rovina Lockman's group. They showed that in desert, when there's a strong precipitation, then this water absorbed in the desert will also sometimes introduce this bias. And if you are on a desert area like Southern California without farmland or vegetations, then usually this effect is less. But again, this is still a very young area of research. I would say if you're interested, keep an eye on the new papers. But this parameter is actually a pretty good parameter for you to have a rough estimation of its potential impact on your study area. And also one more thing is don't really worry about it that much, because actually from all the current studies, this bias velocity is actually really small. If you check all the papers, including UGS paper and Homa Ansari's paper, the bias velocity is actually up to 1 centimeter maxed out. And in most areas in this region, actually, or in UGS papers example data set, is actually within a few millimeter per year max. So it's actually really small. But if small signal is of interest, you may care. But if you're talking about a city substance or volcanoes, your signal will actually usually much bigger than this. Okay, let's move forward then. The next step is actually the phase deramping, which is a data-dependent method. This step is literally estimate and remove a linear or quadratic ramp for each acquisitions of your time series. And by a linear or quadratic ramp, this corresponding to a very large scale spatial wavelengths part. So if you study interseismic deformation or earthquakes or tectonics, then you will definitely don't want to do that. If you study volcanoes, landslides, or city substance, then you may want to do that to make your product cleaner, because that's not your interest anyway. And the next part is the topographical residual from DEM errors. We know from earlier that the DEM error will introduce a phase in the InSAR and is proportional to the perpendicular baseline. And we have a perpendicular baseline time series. So we can actually fit the perpendicular baseline time series to our InSAR time series and estimate the coefficient, and then use that to remove the impact from the DEM error. And there's a paper from Harish Fatahi and Falk Amlang, which is implemented in MinPy, and with options look like this. Besides those complicated options, we can read. The simple one is literally specify, turn it to yes, and then run it, which work for most of the time, except if you have a volcanic eruption in your time series on a big earthquake. Then you need to specify a more complicated options, such as using a higher polynomial or specify the eruption date or the earthquake date in here, so that the fitting will take that into account also. We can just run it. Should be pretty fast. Okay, here it's done. And we can see the estimated DEM error, which looks like this. And you can see it roughly makes sense, right? Close to the reference point, it's pretty small, but if you go to the mountain regions, it's pretty big. This part I actually don't know why it's like that. Maybe because of ionosphere or something. But with this estimated DM error, we can calculate the corresponding topographic phase, topographic residual phase, and remove that from the InSAR time series. And that is what this step is doing. That's why this step actually eventually writes the result into a new time series file called DM error with a suffix like this. So now we did almost all the corrections that I could think of. And then again, all of the corrections are not perfect. So you will again still has atmospheric turbulence left, for example, in your time series. And then one way to handle this is to actually characterize the noise level in a very rough way by checking which acquisition are noisier. By checking the residual phase from the InSAR. We can do that by, for the final time series, estimate a time function or temporal deformation model, and then check the left. The residual then would be everything that we haven't corrected for, or we haven't modeled as deformation. Then those things are the things we consider as noise, and we can calculate a phase residual root mean square for each acquisition. And then we can basically just score each acquisition with an RMS value. If the RMS value is big, that means that acquisition has relatively bigger noise. If it is small, that means the data acquisition are either very well modeled or very well corrected for the potential noise. And of course, then one nice thing with that is we will have a rough idea of which acquisition has less noise and which acquisition has more noise. So one nice thing is we can use that to choose kind of the clean reference date in time. But again, the reference date, the reference in time in InSAR doesn't really mean that much. It just gives us a kind of a clean look when we plot the time series, because it's literally but does not affect the time function estimation or velocity estimation, because changing the reference date in the InSAR time series is literally shifting the InSAR time series up and down along the y-axis. So the slope or the time function estimation of it doesn't really change at all, except the y-intercept, where the y-intercept does not have, in InSAR, does not have any physical meaning. Let's see if there's any questions. I want to check if does everyone's notebook is running okay? Are you catching up with the running of the notebook here? Okay, great, good to know. Great. So you can see here, based on the okay, let's see the result. You can see here, it's calculating the residual R root mean square for each acquisition or epoch, and then find the epoch or the date with the minimum RMS, which is this date. This is the date we will love. And then there are dates with RMS value that is pretty big. How big? It's bigger than the 3 times the median root mean square. It's kind of a standard outlier detection method we can use to find the dates that has big RMS values. And we can plot that shown here. Here, each bar represents one date, and you can see the RMS value shown on the y-axis. And then these black dashed lines are the automatically detected RMS threshold based on this median absolute deviation. And all those gray bars are the acquisitions larger than that, we would count that, score that as noisy acquisitions, and we can remove them or exclude them when we try to estimate the velocity. And the orange bar here has the lowest RMS value, which we considered as the cleanest date. We will choose that as the reference date in time. And this date is written in a TXT file named this one.
There's a question that relates to this, essentially.
Yeah.
Should you consider doing this, changing the reference date if your reference date is noisy?
Yes, I would. Simply because of for the sake of the eye, when you plot them in the times in the using view PY, you plot all of them in maps view, and you will see once you have a clean time series, you will see the signal of interest or other things much cleaner. But again, changing the reference date, which I always do, is only affects the looks, does not really change your estimate of the velocity or other more complicated time functions. We will demonstrate later very briefly. So yeah, so then let's just do that. Okay, so now we have done all those noise corrections. So we want to re-estimate the velocity. Hopefully we can get a better velocity, right? Let's do that. Run the cell. Okay, it's done. Now we can then compare this linear velocity we estimated before and after all the corrections. So we have by far corrected for the phase RP errors and the topographic residuals. For the DM errors, one of them is called raw, one of them is called this name, and you can plot them. You can see these are the results. So these artificial features that we saw before, now is gone. Yeah, that's mainly it. If you turn on the tropospheric correction, you will see more differences. And if you turn on the other corrections or in a bigger area, for example, such as the plate motion or solid earth tide, you will see this kind of slope changes slightly. In this case, it's pretty small, so we don't really see it. But if you have a much larger region, I think this study area is around 50 by 50 kilometers, roughly. But let's say if you study an area of 200 or 1,000 kilometers by 1,000, then you will see those effects very strongly. You can see that actually in those papers. I have actually put the link of the papers in the corresponding sessions if you're interested in. Okay, so we now have the pretty good interseismic velocity. We can see the profile of this using a script called plate plot transaction. This one is plotting a profile starting from here to here. And I can see the profile on the right, where we see a very clear creeping signal crossing this Hayward fault. And this signal is around from here to here in the centimeter per year. So it's around 3.5, yes, 3.5 millimeter per year of fault creeping across the Hayward fault. And you can plot the same thing by changing these values and check the profile on somewhere else. Yeah, so I will stop here for now and let's see if there's questions before we go to the next. Okay, then go to the next. So by far you have actually done everything. You generated InSAR time series. You checked all the errors, and you correct them. And now, sorry, let's see the question. Why the profile looks sparse? it is over a continuous raster. The profile is sparse because of the pixel size. You can see we actually plotted them as point, but each pixel has a size here, right? In this case, in the case of area, the pixel size is around 90 meters, if I remember right. So if you actually plot each pixel as a 90 meters width along here, they will, at least along the distance axis, they will be continuous. This big gap is because, yeah, but this big gap, two of them, they are actually adjacent to each other.
I think it looks more sparse than it really is, just because of the vertical separation.
Yeah.
We have creep because we see this sharp difference. Basically, yes, that just means that you have a relative motion at the surface that is manifest over a very short distance. And that is one of the signatures of fault creep in InSAR data. It's kind of a very sharp contrast in velocity across some linear feature.
And usually if I see a creep like this, I'll be thrilled as time to write a paper.
Absolutely.
And again, yeah, you can see this creep here, clearly here, and here. So we don't see it very clearly here, but we will later see that we have it here.
It's
Also.
not creep there though. That's
Right.
that's relative aquifer motion bounded by a fault, and it confused a lot of people because it looked like the fault was moving forwards and backwards seasonally, but it was actually
How fascinating would that be if that's true?
yeah, that'd be amazing. Or actually, the Hayward fault did move backwards in response to the Loma Prieta earthquake for about there was a very, very minor backward movement from the stress change, which just means that the friction is really weak.
Oh, interesting.
Yeah, there's a Nature paper about it from like
Wow.
1991.
Could you share a link of that paper? I would love to see it.
Yeah,
Actually.
by Jim Lee and Camp. I'll find it.
I did not. Shoes asked. I did not see anything about the InSAR measurement point. Oh, could you say something about that? Yeah. When we're talking about the point or pixels, it's actually the same thing. Even in the PS analysis or DS analysis, you see it in the European groups mostly. They're plotting everything in terms of the points, but they're still actually pixel size. In this case, they are still actually in terms of like a raster, like a matrix. Of course, each of the point can still has the lat and long. It's just a plotting thing. I can plot this instead of a 2D matrix. I can plot them with each of them as a point, and then they can have some separations, but it's the same thing. Those points actually, only if it's a PS point, then PS point in physically corresponding to a specific structure, it all has a really a point. But if it's a DS, it is really a grid with size. To me, is a real physical, realistic representation. Okay, let's go to the last two. So once we have done InSAR tensor analysis, a lot of times you want to validate it. And in this case, we can validate that using GPS or GNSS. And note that before this step, we haven't really used any GNSS data, right? So the MiniPy results or products is actually independent of the GNSS observations. That's why we can use it to validate our result. And in this case, we are downloading by default using the processed GPS daily time series from the University of Nevada at Reno. They have the dataset from Global. And we can just run that using the View-to-PY. Let's just run this cell, and you can see it's downloading a compiled list of all the names and latitude and longitude of all the GPS globally. And based on that, the code will do a searching based on our InSAR data coverage and the time coverage, choosing the ones that overlaps in both, and download those GPS daily time series one by one, and then project this GPS time series from east, north, up direction into the radar line of sight direction. Then we can compare the two in a common space. Oh, and also for this comparison, the code is referencing the InSAR data into the pixel that is nearest to one of the GNSS stations, so that they are also in the same spatial reference, which is specified here manually using this option P225. And you can see the result here. Let me zoom out a little bit. Yeah. And we can see each of them, of course, are the names. So you can see that overall, the circles here represents the value from the GNSS, independent of InSAR, except all of them, they are referenced to this station here right now. And you can see these circle colors and the independent InSAR result, they are actually overall matching with each other pretty well, except that you can see some of the values here normally are very different. These values here are also very different. Then we can see how they look like. We can do that by plotting a profile. Well, the profile like this, where the x-axis are the InSAR results for those pixels co-located with GNSS, and the y-axis are the GNSS velocity. You can see two of them matches with each other pretty well, except you can see there's some values point here or here are very off. And the code will do actually a very preliminary outlier detection. By far, the fitting is not very good. You can see even with very bad R-square value, the coefficient of determination value. We can again do the standard outlier detection using the median absolute deviation, and then by using that, very preliminary, you can do your own ones, of course. They find these few GNSS sites has very different values between InSAR and GNSS. As you can see here, they're all pretty different, larger than 5. I think this is larger than 0.25 centimeter per year. And just for fairness, we can remove or exclude these sites from the GNSS. From our comparison, you can actually just uncomment this line. You can exclude these few sites as listed here and then rerun. You will see now the coefficient of determination now is like super high, which to me is a more fair parameter to say these two are actually comparable. And of course, you can actually, for those few sites, you can see what is going wrong there by checking the Nevada website. And go here, for example, we know, for example, these sites has problems. We can just come here, do a search, these sites is here, and go there and then check their website. And then you can see the time series. Let's check another one. Let's say this one. Back, check this. And you can see this site is actually has some problems, right? We have a data set from 2015 all the way to 2020, and these are the GPS time series. And this time marks the, I think this time marks the Ridgecrest earthquake, but this whole time series is not fitting well. That's why I don't know what's actually the issue here.
Yeah, they have this 1 year offset estimator thing that they run that compares the data 1 year apart, and they use it to find these kinds of steps, and it doesn't fit very well.
Yeah. So
knows?
basically, yeah, so in practice, you will find a lot of some GPS data sets or the velocities sometimes does not make sense. This is the kind of way that you need to go dig a little bit and then exclude those from your validation.
There's a question. If you have your own GPS velocities, how can you import them?
Building functionalities, no. But as you see, the product from MidPy is essentially that time series, that the H5 file. It's a H5 file, standard H5 file, so you can read them using Python, MATLAB, whatever you're comfortable with, and then do this type of simple analysis yourself. Okay, so one last thing is for this session is finally a time function. A time function because by far we have been feeding our InSAR time series with a simple linear line, but in reality, especially if you're a geophysicist, you want more complicated processes, such as the earthquake, especially the post-seismic deformation or pre-eruptive volcanic deformation. And in those cases, you want more complicated time functions beyond the linear slope. And there's a very nice paper from Eric Hedlund et al. That defines a lot of time functions, as you can see here. Well, you know the B-spline for now, but is with the red and purple ones, which is exponential and logarithm time function, which is very commonly used for to fit the post-seismic deformation. And thanks to Yuankai Liu from Caltech, we have actually implemented most of them into MidPy directly. So you can feed and run this time function feeding to your InSAR time series very conveniently. And these are the currently supported time functions. You can use a generic polynomial. Just be sure we're on the same page. For polynomial, if it's polynomial with an order of 1, represents linear. If it's 2, it represents quadratic or acceleration. If it's 3, it's the acceleration of the acceleration. Or you can use periodic, which you can use to define the annual signals, semi-annuals, multi-annuals, whatever you want. Or you can specify the step function, which usually can represent the eruptions or the jumps, such as an eruption, earthquake, or actually if it's a sudden move from the landslides, for example, and exponential and logarithm for post-seismic usually. All of them can be defined with some explanations here. And in this case, we will choose our time series that we estimated and then play with it. And we can play with that usually because you don't really you don't really know your time function in advance. So one way to do is to play around with your time series in time and then see what would be the representative time function behavior of your dataset. And in here, we're using another script called TSView. This is one of your another best friend. In MidPy, you can use that to play with the time function. In this case, let me zoom out a little bit. See things. In this case, you can move around and then let's say you can click one here. It will plot a time series look like this with a simple linear fit. And the linear fit result is shown here. And this is one that is super close to the reference point. So it's very close to 0, which makes sense. And then once you are crossing the Hayward fault, comes to here, you'll see around a 3 millimeter per year of a slope due to the creeping across the Hayward fault. And you can cross the Bay Area, come to here. Then you can see more scatters, and you can see this scatter actually has some annual seasonalities here, which is a sign that shows us that you might want to fit an annual signal in your time series. And you can see here, let's say, then in here you can see a stronger signal. But to me, the most interesting one is actually this aquifer. This aquifer, we have been updating the time series for this class for several years, and this aquifer changing is pretty amazing. So in here, we see an acceleration, a flattening, a deceleration. Now it's flattening again. I don't know what's the jump here, but it's pretty complicated. That means usually, for example, identify means that we want to either fit a more realistic physical model or generally use a higher order of polynomial for our fitting. Okay, so we now examine a few. We know that we want to fit a linear. We want to fit a polynomial because of aquifer here, and we want to fit an annual because of the behaviors here. So let's just do that. You can do that using this function, this script called time series to velocity, and then specify the polynomial with order of 2, annual signal with a periodic, which is a period with 1 year, and we can save that into another file. Let's just run it. And you can see it reports the specified time function parameters that we used, that we specified. Again, these two. The others are set to empty. And we can see it saves those estimation results into a lot of data sets. The velocity we have shown, the velocity standard deviation, the acceleration, its standard deviation, and for the annual signal, we have the annual signal's amplitude and the annual phase. And we can plot them by clicking the cell below. As you can see, let's zoom out a little bit. So these are the velocities. These are the linear velocities. Its acceleration, the annual signal's amplitude in the unit of centimeters, and the annual phase in the unit of radius. And in this case, is since we're having a period of 1 year, so this is basically from here to here. The 2 pi spans for 1 year. So yeah, the period function, if you check the definition there, the period specifies is specified in the unit of 1 year. So 1 is annual, and then the semi-annual would be 0.5, or you can change it to other things. So no worries. So we can see that again, if we fit this whole thing with a more complicated signals, more complicated time function, we can see much more interesting things. We see the overall very high substance in this aquifer. We see a high, sorry, this is an uplift. Yeah, this is an uplift here. We have another uplift here, and we can see this uplift actually has a de-acceleration trend here. And then you can see also in this aquifer, even though there's uplift and de-acceleration, there's also a pretty big, there's also a pretty moderate seasonality here because of this amplitude. The blue one is almost 0, which means there's no seasonality. In here, there's seasonality, and here too. And we can actually see some even interesting that the phase, that means the seasonal behavior actually has some spatial variation. There's a very nice discussion regarding the phase of the annual signals in both Brian Ryle and Mark Simon's paper on Los Angeles Basin, which Paul showed earlier, and also on a few papers from Ravina and Lohman's group that you can check if you're interested in, which has actually really fascinating results. So that's it. Before we go to the end, I just want to show you one last thing, is that for all the notebooks that we see here, we're running everything in cell by cell, but you can actually run everything all in one command line. Let me show you just literally very simply how to do that. We have the UNAFCO environment or any contact environment that later on you will have. So in the Linux, we go to the MinPy work directory. We have all the files, and we have these custom configuration files. If you open that, that's all the options that we specified. The reference point, the topographic error correction, the unwrapping error correction. And instead of, if you are getting more and more familiar with MinPy, if instead of running this notebook one by one, you can run everything by just typing this and run this in one command line, then you will do everything as shown in the notebook for you. So in reality, when you run notebook, when you run the MinPy, all you need to do is really get familiarized with the template, with options in the configuration files, and then set up your configuration files, and then you just rerun this one line over and over until you get a satisfied result. And a nice thing is this auto skipping strategy implemented So if you are changing a parameter in a very late stage, the earlier stage are the same. The code will automatically judge that and then skip all the unnecessary rerunning. And then you will just skip the first and then go to the change place, go to the step that is changed and start from there. So it's really convenient. Yeah, as you can see, it's running everything, almost everything already into the end. Yeah, so it's just want to know that. And a few other features that I will not demonstrate. You can check if you can check after the class. One is the parallel processing, which is very useful if you have big data. And then once you turn on the weighting, also a few visualization scripts. View PY we have already showed. TS view, which is also very useful. We have already seen. Plotting the plot of the transaction ones, or you can save them into the Google Earth as a KMZ file also for both the map of the velocities or the time series with interactive plotting also. And you can project the line of sight into the from ascending descending into the vertical and horizontal as Garrick demonstrated previously. You can do the mosaicing if you have multiple tracks and then stitch them into a much bigger area. And then you can export them into other formats that are for geophysical modeling or for GIS or for sharing. So the homework for this session would be it's also written in the syllabus, is to rerun the whole process, manually choosing a different reference point because it's important, and turn on the tropospheric correction using PyAPS. And note that you will need to register for the ERF5 website and then testing that as shown earlier in the GitHub desktop in the GitHub website, which is here on the PyAPS. The link is also on the notebook in the PyAPS website. If you go to the second part of the README file, there's a account setup. You need to go through all that to make sure you can download the ERF5 dataset for tropospheric correction, and then turn on the third is turn on the solid Earth tide correction, which is just adding another template options into your configuration file. This is homework part 1. Homework part 2 is to play with the time function fitting. As you see it here, try, for example, adding more time functions, such as the semi-annual, or adding a step function like that, and then show your estimation result. You can check the appropriate time function again using the TS view, here by clicking and seeing what will be appropriate time function for your dataset. Let's see these questions. Yeah, this no lookup table. It's just a warning. It's fine because lookup table is something that is really used for the dataset in radar coordinate. We want to use that to connect the radar coordinate with geo coordinate. But in this case, the area product is already geocoded, so we don't need the lookup table. Yeah. Let's see if there's more questions.
Well, we have one more thing to cover, right?
Yeah, that one should
And maybe
be fast.
we should take a short break.
Yeah.
Give everyone a chance to recover.
Yeah. Let's take a break. 3 minutes or 5 minutes break?
8 minutes,
Sounds good.
2:10.
Okay, let's come back at 2:10.
Well, I think we have one more thing to go. And that is the stack processor. So if you wanted to import your own data into MintPy, and it doesn't exist on ARIA, then there is a way. And the engine is going to tell us how.
Do you see my screen?
I do.
Great. So yeah, yeah, exactly. If you find in your study area there's no ARIA products, one way is to generate that yourself. The other way, actually very nice, is to use the SF on-demand processing. They can process it for you also. This is the option one. You can generate that using ICE. And in ICE, we have demonstrated from the first few days the pairs processing, where we use the TOPS app or strip map app to generate pairs of infograms. Oh, sorry, I actually flipped it. Sorry about that. This line is representing this figure, while this line is representing the top figure. We can use TOPS app or strip map app to generate many pairs of infograms. That is actually what ARIA is doing, what Lixar from Comet in UK is doing, and also what the ASF HP3 on-demand processing is doing. And as we note already, the pairs of infogram is different from the stack. So go. Franz, want to say a few words?
No, I think I blinked up because of the Slack message that came in. So no mind.
We know that the pairs of infogram is not exactly a stack, so that's why we need a few preparations, usually the stitching and cropping, to make them consistent to generate this stack of infograms, and then we can do the time series analysis with MinPy. And as an alternative way is to do the stack processing. And in this case, the major difference is instead of generating pairs of infograms, we generate a pairs of co-registered SLC first. And then from that, you can generate whatever pairs or networks of infograms you want. And this code is available in ICE2, and there are actually 3 types of stack processors. The top stack for the Sentinel-1 TOPS data, the strip map stack for all the strip map data, including a lot of old data sets such as MVSAT, TerraSat-X, Cosmos SkyMap, etc. And there's another called ALOS stack. The first two are mainly developed by Harish Fatahi and Piyush Agram. The ALOS stack is mainly developed by Chuiren Liang, while during his time in JPL and Post and Caltech. All of them, they are available, and all of them will generate a stack of co-registered SLCs. And then we will demonstrate in this session how to do that. The benefit, of course, is the stack processing is much more processing efficient because it's more processing efficient because it runs this topo step only once. If you recall, in the TOPS app, this topo step actually takes us the longest time. And instead of, if you're doing TOPS app, you will run this for every single pair, while if you run TOPS stack, you will run this only once. So it's much faster. And also because we are generating a stack of SLC, so all the SLCs are actually more consistent in terms of the precision and aligning. because of the network redundancy, similar to the time series analysis fashion. And if it's a co-registered SSC stack, you can actually run not just MinPy, you can run other softwares also, such as Stamps and Fringe, the new one, which does the PS and DS analysis. So in general, a stack processing will make the result more consistent and will allow even larger freedom for the later words time series analysis also. And the stack processors are all already on GitHub on the ISCE page. In the ISCE page, let me go through this. In the ICE, if you search ICE GitHub, we'll go to the ISCE page. And in the ISCE page, the README file is scroll down. There's a running ICE stack processors. Click here. It brings you to all the stack processors, the three we just described, with the installation note of how you need to install ICE. Besides the usual installation, there's one more step to do some path setup. And there's references for various stack processors also. And the references for Elo stack is within here. Okay. The general idea is actually the processing in terms of the workflow is actually exactly the same as the pairs processing that we have practiced for. So all your knowledge is exactly the same, except some optimization for the large data processing with the stacks. This is the workflow for the top stack. This for the strip map stack, sorry. And then another thing is with all of them, the strip map stack, top stack, and Elo stack, all of them now includes the ionospheric correction using the split spectrum. So you can run that also if you like. These are the result of the ionospheric estimation from the strip map stack from Heresh's paper, where the first row are actually the raw InSAR time series. The second row are the ionospheric delay, and then the third row are the corrected ones. And this is for A-loss, and it's L-band, so there's a lot of ionosphere as you see here. That's why it's actually pretty critical if you are using L-band data, including if the future NISAR to correct for the ionosphere. Similar things for top stack, except one thing that top stack usually requires a higher precision of co-registration using the enhanced spectral diversity or ESD method. And it's also, you practice that in TOPS app, it's also included in TOPS stack. Again, you have each of them has a README file for the tutorial of how to run them. I will demonstrate shortly. Just one note is that the TOPS, all the stack processor are not notebook friendly. So you basically kind of have to run them. You kind of have to run them in command line in terminals, and it does requires a familiarity with Linux and Python programming. So yeah, so it's a relatively steeper learning curve. Okay, so that's basically this part. And now I will just demonstrate how to do the stack processing. I wrote a final note for the top stack. If you click here, the README file, it shows literally step by step of what you should run to get a stack. Okay, and then now I'll just demonstrate that. If we, sorry, let me just bring up my notes. Okay, now I'm in a workstation, a very small one locally, and now I want to warm up or activate my Conda environment using Conda activate in AppCo which is the same one that I installed locally. It includes the ICE2 from Conda Forge. And then besides that, I also need to add an extra task setup to the stack processors. And the stack processors by Conda, there is a ICE stack environment variable, which is already set by Conda. So we'll just do that and then add that to the environmental variable path. After that, you will get this stack processor ready. And cool. I think I need to do instead of iStack, top stack. Yeah. Now the stack sentinel is ready. This is basically the main script that I will use. If you check the help message, it will generate a lot. And you can see there's a lot of options. Unfortunately, you have to, it's highly recommended you learn all those options because the stack processing involves a lot of data and a lot of files and a lot of steps. It's important you know every single options to do a proper setup in the very beginning. And I'll show you how. This is first, and now we also need to set up a few auxiliary directories to save the orbit files and the calibration files for Sentinel-1. In this case, I put my files in this directory. In this directory, I have two files. One is for the auxiliary file, the calibration one, the calibration for Sentinel-1, which is needed. And the other is the orbit file for Sentinel-1, which is a lot here. So you just need to do the two. And now you will usually need to go to the SF website to download the data, which in this case, I already downloaded the one. Actually for the Salton Sea. I have downloaded a lot of SLCs from ASF. If you check, it's actually huge. And I have downloaded a few DEMs. I think currently DEM from ICE2 has some problems, but you can use the SAR DEM generated, developed by Scott Stanwitz from JPL. That also works and installed in the Renavco instance. And in this code, we'll just download the DEM from Copernicus and then prepare that in the format that ICE2 is expected. So in this case, we generate a DM folder already existed. We go to the DM folder and then prepare the DEM. I use SAR DEM with a bounding box. In this case, under this bounding box, you have to choose it yourself, of course. For the bounding box definition is around here. You can choose. In this case, I use a 5 by 5 degrees area using Copernicus as the DM source, and then prepare that in the ICE2 expected format. This may, let's see if it's taking 10 minutes. Five by 5 DM is actually pretty big, so it might take a while. Let's just go to another tab, check what's going on. So you see in this folder, the SAR-DEM is downloading the Copernicus and then save that by default into a file like this. I actually have already prepared another one, so saved in a slightly different file, look like which is this. So I will just use this one instead. Again, before I need to set up the path. Up stack. Okay, we have prepared the DEM. We have downloaded SLC from SF. And now we should just run top stack. And one thing to note that is you can download DEM, download SLC using the bulk delay, using the bulk downloading script in Python, or actually using Sarah. I found that Sarah works pretty fine, works pretty well still for Sentinel-1, not sure for other things. And in Sarah in here, you can actually specify the program, specify the platform with the relative orbit number plus a bounding box. And in this case, if I use that, if I use Sentinel-1, let me just copy it over, it's pretty long. These are the ones that I used. I specified the Sentinel-1 A and B. You can combine them with no problem at all. These are the track number that I used. These are the bounding box of my study area, and I just do a print. This will show how many data available for this criteria. And then I can rerun this script using download to really download them. Yeah, so you can see there's a lot of them. And then you can change this to download, even with a parallelization. Let's say parallel 4, and then you can download it in parallel. Okay, now we have those two prepared. Let's just run the Slack Sentinel. And again, check the help. With the Slack Sentinel, you want to specify the directory of SLC, which is here. The orbit file, which is here. If they are not downloaded, don't worry, the code will automatically download it on the fly for you. So all you need to do is really just specify the folder. This is for the calibration file, the DEM file in the ones that we just prepared. I'm using this one. The call registration method. There's two methods that I have learned, the geometry one or the ESD. In most of the case, I just use geometry, which is actually accurate enough for most of the applications. And then we can specify the subsource number. In this case, I will use 123, or you can choose whatever you like. A bounding box. And this bounding box is important that you want to specify the same bounding box while you type in here, and the same one you used to search in SF. Otherwise, sometimes because of the frame varies through time for Sentinel-1, if they're not the same, sometimes you will find that there's some burst data that is missing during your downloading, during your searching and downloading, and then in this case, you will find there's errors laterwards in the processing. This is also the reason why I like the Sarah searching, because I can specify the bounding box here directly instead of using the polygon. And then we can specify the workflow. And for this top stack, you can generate a stack of SLC, or you can use the infigram workflow, which includes the stack of the SLC and then plus the infigram and unwrapping. So this, which in the infigram workflows is what MinPy is needed. And then for the infigram, you want to specify how many connections you want to generate. Most of the time I specify 3 or 5. I personally like 5. And for each infigram from the full resolution SLC, you will usually want to apply a multi-looking, either to increase the signal to noise ratio or reduce the data volume. This parameter depends, of course, on your signal of interest to the sides. If it's a very small signal of interest, you want to use low number to keep the resolution. For me, if I'm studying tectonics, I'm pretty fine with low resolution. I even try 10 and 30, have 300 looks, which is usually much faster. For each interferogram, before unwrapping, you will apply Goldstein filtering, and the filtering strength is from 0 to 1. So in this case, I specify a 0.5 filter strength, and then you will apply, and you can specify the unwrapper. The unwrapper in ISCE2, there's a few unwrappers. ICU, which is pretty fast usually, as shown here, and snafu. I will just use snafu by default, and then run it. So there's a lot of information. Let's go through them one by one. You can see after the run, the script finds there's around 700 save files, all of them covering the bounding box, which is nice. In total, we have around 240 dates. These are the date list, and these are actually the scene center of each date. In the end, it will show the overlapping region among all the downloaded save files, which is this one. And of course, you want to make sure your specified bounding box is within this one so that they are fully covered. As you can see, all the dates are this much, and the date that covers the bounding box are the same. And then after that, by default, you will choose to co-register all the SLCs into the first date by default. You can change to a different date, but it does not really matter much. And then after all that, this script will write a round files, look like this, and you can see now how the folder looks like. The save file just TXT file list all the save files besides the DEM and SLC. We have two new folders. One is a round file. Let's go inside of it and check. So this is literally how you run it. After this round file, all you need to do to run a stack processor is to run each of the stack files one by one until the very end. Then you're done. And you can see these steps are actually corresponding to the steps we have learned through TOPS app. Again, they are the same thing, just do it in a stack fashion. And if we check for example, the last one, let's say, the last one is to unwrap the interferograms. If we look inside, it's one interferogram per line. And then there's a configuration file in the configure folders. And let's go back to check that. We can see it's one line per pair. And then we're repeating that to, in this case, we are generating actually over 1,000 interferograms. And the configuration file is inside the configures folder. If we check, there's a lot of configuration files. And if you check one of them, this is a configuration file for phase unwrapping for this specific pair. You can see these are the input, these two are the output. These are more detailed configurations we have specified, such as the number of looks, the unwrapper using snafu, etc. So all these are determined when we are running the stack sentinel script. So that's why we really want to learn all the options provided by this. And yeah, so that's basically it. And for anyone, if you are experienced HPC user, you can do the parallelization, because you can do the parallelization for each of the scripts. For example, this one, we have over 1,000 pairs of interferograms. Each of them are actually independent. After you finish the previous step, then you can run those theoretically, those 1,000 interferograms in parallel. Then you can speed up significantly. Of course, it depends on the process, it depends on the computer, how big it is you have. And after you run all this, the result, let me just show you briefly how the result looks like. after you run this data set, which is what I did previously, you will have a folder looks like this, which generated much more folders. And for time series analysis, what you really care is these two folders. One is the merged one, which has all the data set that is merged. And in this case, both the SLCs, the geometries, and the interferograms. In this case, you can see there's a lot of interferograms. If you go to any one of them, you have, we have a lot of other files. I deleted all of them. The remaining ones that is needed is the unwrapped interferograms, the corresponding kinetic component, and the spatial coherence. So then what we need to do is, after you have all these, specify this path in MinPy, and then you can run MinPy just like that. And the corresponding ones, let me see, just bring up again the MinPy repository, MinPy GitHub. Go to the first one. Go to the MinPy documentation in the example directory structure. This, the first one, is the exact same structure we just shown. And then all you need to do is using a slightly different path pattern for all the same data set that you just used, like area tools. And you can repeat the same process for all the other different processors. That's it. Any questions? Or anything unclear?
The only thing I would have maybe added would be that you can run stacks for different purposes, right? So
Yeah.
you can output just the SLCs, you can output dense offset maps, all that kind of stuff.
Right. Thank you, Greg. That's a great comment. In here, there's a workflow. What we used is interferograms. You can actually just generate a stack of SLCs, or you can generate a stack of correlation, or you can actually generate a stack of offsets. They are working in a similar fashion, but all of them are actually built on top of the co-registered SLC. Okay.
Yeah, I think so. Great stuff. That's a great reference for anyone who wants to run these things. Go back and watch the video over and over again. But the documentation is good. I've tried it a few times. Let me see. Can remove the spotlight from the engine now.
Next year we can have a notebook.
Sorry, Paul, didn't hear you.
You said maybe next year we can have a notebook.
Oh, yeah, that sounds nice, actually. Yeah.
Okay.
Excellent Yunjin show at the end of the course.
There's a yeoman effort of several hours of instruction. Go and have a lie down now.
I need.
Right, so that was the last module that we're covering. I'll share my screen and put on where we're at. Does that work? Oh, that's not what I meant to click. Okay, this is where we're at. Zoom in a bit here. All right, so closing remarks and preparing for post-course activities. As Yunjin mentioned, he would like you to do some things based on what we've looked at today. They're laid out here. The first is to reprocess the InSAR time series by adding by changing some things. Choosing a different reference point with a justification, applying some kind of troposphere correction. The suggestion would be to use ERA5 in PIAPS, but you do need to register an account with ECMWF if you want to do that. And applying a solid Earth type correction. Run those corrections and look at the output and see what they're how they're different from what you started with. And also then the second homework is to try applying some different time functions for your displacement time series. And there are a bunch of possibilities there. Annual functions, step functions, and so on. And I guess you could justify your reasons for choosing the one you do. And save those outputs as PDFs and put them in the homework folder. Is there anything else you'd like to add, Yunjun, to that?
That's perfect.
Fantastic. Post-course material in general, on the syllabus, when it's finished, and it's very close to being finished, we're just fine-tuning one question on the final version of it. There will be a post-course survey that includes the theoretical practical questions we asked you before, as well as a series of a short number of questions about what you thought about the course. And please all do fill that out because it will be very, very useful to us in continuing to develop this course for the future. I will edit this in a few minutes to include like what we have said about the homeworks and when we would like them submitted. And we'll also provide some information here when France's people get to it about how to install ICE through Conda and also how to install the UNAVCO environment through Docker. Right, France?
Yes, so the Docker container will be ready by the time we shut down the service, which will be roughly in a week from now. We are currently planning to do that in a week from now, so probably Monday. Well, let's see, let me check here. So today is the 26th, so we're currently planning to shut the service down slowly on the 5th. If lots of you are not quite done yet, please let us know in time so that we can add a few more days. And by the time we shut it down, we'll have a Docker solution for you that you can install locally with all the latest releases from MinPy and ARIA tools and ICE installed.
Brilliant. So that's what's coming. You will probably see some emails from Melissa with some of these details as and when we firm them up. And all that remains then is to thank everyone for coming by and taking our course. It's always a pleasure to try and impart our knowledge to interested people. And you've been asking lots of great questions, which gives us some pride that we're actually communicating with you enough that you're actually able to ask us detailed technical questions about what we're doing and how to do stuff. That's really fantastic. I'd like to thank the UNAVCO staff, although they've all dropped off the call. So if Melissa watches this back, she's been fantastic, and Becca as well, in setting up all of the stuff behind the scenes. We wouldn't have been able to do it without them. And similarly, our TAs and other instructors who have been chiming in with useful information all throughout or running sessions. Again, we're very grateful for all their efforts. Is there anything you'd like to say, Franz?
Maybe just in addition, so we didn't meet you in person, so but it's likely that we might run into each other at I don't know, AGU or IGARSes or conferences in the future. If that's the case and you recognize any of us, please say hi. It's since the pandemic, a bit frustrating to not know and meet your students regularly. So if you do run into us, please say hi. So that we can connect also more personally than through Zoom.
And if you have questions that are outstanding, and I'm seeing some being posted in the chat now, a good place to put those questions would be on Slack. We will still follow it for some weeks following this course, and we'll roll you over into a more permanent Slack forum where you can raise questions as they occur to you. And our goal is to have that be persistent for all future course participants. So we will build a kind of a user base on the Slack channel that you can try and use as a resource for getting your questions answered.
Yeah, and remember, so all the recordings will be remain available on YouTube. So if there's something that you can't quite remember, you can always go there and rewind, you know, to the spot where you sort of lost track of what one of us said. So that's a resource also that's going to be at least permanent for the next few years.
Yeah, I would like to add for beyond this class, if you still keep using ICE or MinPy, they have their user forums. ICE is on the GitHub discussions. MinPy has a GitHub discussion and the Google groups. You can go there and ask questions or have answer other people's questions also, which will be really much appreciated.
Fantastic. So with that, I think we can declare the course over. And we can all have a little rest. I'll see some of you next week at the InSAR meeting. And as I say, please do say hi if we run into you at other conferences. And we hope to do so in the future. Bye.
Bye. Friends, I actually don't know for the Docker.